What if nothing isn't empty at all, but a place where our usual words before, after, space, time don't apply yet? The question sounds dramatic, but the work is technical. How can a universe begin if there isn't a before to begin from? Think of a room that has no walls until the light comes on. Once there's light, wall becomes a meaningful word. That's the spirit here. No mystique, no hand-waving, just how the rules of physics can let a description of the world switch on without needing a prior stage. In this story, nothing means a pre-classical regime where before and after aren't useful labels yet. From there, a lawful handoff leads into the ordinary stage, where space and time make sense. And that handoff isn't perfectly smooth. It carries a tiny fingerprint in it, irregularities that act as the seeds of everything that follows. We can still read those seeds. A faint afterglow of the young universe wraps the sky, almost uniform, but dusted with slightly warmer and cooler spots. Gravity leans on those small advantages, sketching a vast web of galaxies. There's a gentle preferred spacing and echo of early sound, and the light that reaches us is nudged by the mass it passes. Put the clues together, and you get a story that runs both ways, from the beginning to the sky, and from the sky back to the beginning. No drum rolls, just clear steps from definitions to evidence to mechanisms. If the title caught your curiosity, the path is simple. Make the question precise, follow the data, and see why an origin without a before can make sense. When people hear from nothing, most picture absolute absence. No space, no time, no rules, no possibility. That picture is powerful as poetry, but it isn't something physics can work with. Physics is a craft that lives on rules and consequences. If there are no rules, there is nothing to calculate, nothing to test, nothing to compare with the sky. So the first step is to change the meaning of the word in a way that keeps the question bold, but makes it answerable. There are three very different nothings that people mix together. The first is familiar in laboratory talk, the vacuum of a field. That's the lowest energy state of a field in a region of space and time that already exists. It is not truly empty. The field still has jitter, and what counts as lowest energy depends on the shape of space and time you're sitting in. Useful, but not the kind of nothing we need for an origin story. The second is the one that matters here. No classical space and time yet. Before the stage appears, the words before and after aren't just hard to use. They aren't the right language. You can still have rules, just not a rule book written in the usual coordinates. The job is to describe a lawful way to pass from that pre-classical regime into the ordinary stage where space, time, distance, and duration make sense, and to see what fingerprints that passage leaves behind. The third, nothing, no rules at all. Only void is outside physics. That's not rudeness. It's a boundary. Physics begins the moment you can write a rule down and ask what its consequences are. If you remove even that, the subject has no place to stand. Once you replace nothing with no classical stage yet, the headline question stops being a riddle and becomes a plan. Describe a lawful handoff. Say what that handoff must leave behind, and look for those leftovers in the sky. The leftovers, as we'll keep seeing, are tiny irregularities, small, simple bumps in an otherwise smooth beginning. They're important not because the universe likes untidiness, but because those bumps are the seeds of all later structure. If the handoff left no bumps at all, there would be no galaxies, no stars, no chemistry, no us. This way of talking also changes how you think about cause. In everyday life, a cause is an event that comes before another event and brings it about. If the earliest regime doesn't have a usable before, then what caused it? Isn't the right kind of question to ask inside physics. What you can ask is whether there is a lawful relation between a pre-classical description and the classical world that follows. That relation is not a shrug. It's something you can try to calculate and then confront with evidence. The pre-classical regime can be pictured in a few different, equally honest ways. You can think of it as a very general catalog of possible proto-universes, each described by some minimal data, with a rule that assigns weights to them. You can think of it as a deep level where geometry isn't yet a smooth fabric, but an outcome that appears when many underlying parts line up like a picture that only emerges when you step back from a mosaic. You can think of it as the place where the usual split between space and time fades, and only later does one direction take on the flavor we call time. None of these metaphors is perfect, but each captures a piece of the idea. Before the stage appears, you don't have the stage's coordinates, but you still have structure you can talk about. If that sounds abstract, it helps to anchor the discussion to what makes contact with the world. A good origin story does two things at once. It gives you a tight, minimal description of the earliest state that deserves to be called from nothing in the new sense. And it pushes forward to things you can read off the sky, a nearly uniform afterglow of the young universe with a fine speckle laid over it. A web of galaxies whose statistical texture matches what those speckles would grow into. A quiet preferred separation among galaxies that remembers early sound. A tiny, systematic bend in the paths of background light as it crosses the cosmic landscape, and a late-time change in the pace of expansion that has to be folded into every line of sight. A story that takes you from a crisp start to all of that, without special pleading at every step, earns the label from nothing better than any slogan ever could. The most slippery part of this agenda is time itself. We use time words constantly, and we carry them far. It's hard to set them down. But the earliest regime forces the issue, because time as you and I use, it is tied to the stage. A clock is a physical device. It works when there's a dependable background against which change can be counted. Swings of a pendulum, transitions of atoms, ticks of a quartz crystal. In the pre-classical regime, there may be change and there may be rules, but there isn't a background that lets you use the words before and after in their usual way. When the handoff produces a smooth, heavy background, when the stage switches on, then ordinary time appears as a way of labeling change. From that point onward, all the familiar talk is fine. Before that point, it isn't. That difference doesn't make the beginning mysterious. It makes it careful. If you insist on asking, what was before time, you will tie yourself in knots. The better question is, what is the lawful relation between descriptions that don't have classical time and descriptions that do? Answering that is how you get a usable story. In that story, the handoff is central. It is not an explosion at a place. It is not a spark out of a true void. It is a lawful passage from a regime where our coordinates aren't the right language into a regime where they are. And because the handoff is not perfectly bland, because it lays down tiny irregularities, the later world has something to work with. If the irregularities are simple in the right way, neither tuned nor tangled, they grow into the sky we actually see. What does simple in the right way mean? It means that across a broad range of sizes, the bumps have about the same strength, with only a slight lean. It means that the ups and downs are almost as uncorrelated as the tosses of an honest coin, no hidden patterns that can't be explained by ordinary growth under gravity. It means that there aren't odd, preferred angles or directions baked into the pattern. Those properties sound technical, but they can be conveyed plainly. The beginning doesn't pick a favorite size or draw a secret picture. It sprinkles tiny advantages evenly and lets growth do the rest. The payoff for that simplicity is that one seed pattern explains many different kinds of evidence at once. Once you accept that nothing means no classical stage yet, a few familiar objections lose their bite. Doesn't creation out of nothing violate conservation of energy? In a setting where the entire stage is changing, you can't define a single, universal energy meter that every observer agrees on. What is sharp and true is local bookkeeping. In every small region, Energy momentum is balanced exactly by the equations that tie matter, light, and geometry together. Beyond that, gravity's contribution to the balance carries the opposite sign to the contribution from matter and light. In a closed accounting, the two can cancel. That doesn't produce a universe. It removes the need to pay for one with an external budget. The mechanism is still the lawful handoff, not a debt forgiven by a cosmic banker. Here's another. Does from nothing mean there was a magical jump, so we can never understand it? No. It means you switch from one kind of description to another at a place where the old one fails. That switch can be very concrete. There are proposals in which the earliest region has no sharp edge, so the notion of earlier simply isn't available there. There are proposals where a small, smooth region that can expand is selected from among all lethal options with a calculable weight. There are proposals where a prior contraction irons away wrinkles and a high-density turnaround avoids disaster. They're different routes to the same table, a classical stage with a simple seed pattern laid down. We'll get to those routes in detail later. The point here is that each route can be written cleanly enough to push to the sky. It's natural to wonder where the rules themselves come from. Why these and not others? That question is fair, and it's patient. It doesn't need to be answered before you can make progress on the origin question. The habits, the rules we use could be fundamental, or they could be the effective behavior of something deeper that looks very different at small scales. Either way, if they are the habits that actually hold in our world, they are the ones that matter for the handoff. As you tighten the seed pattern by reading the sky, you don't just improve your origin story. You specify what any deeper account will have to reproduce. You're not dodging the why. You're making it sharper by narrowing the target. At this point, it's useful to give a short, concrete sketch that shows how modest the demand is on the beginning. Imagine an early state that is as smooth as you can make it without turning off all structure forever. Imagine that in that state, small bumps are sprinkled in a way that is as featureless as possible. No favorite directions, no favorite pattern, almost the same strength across sizes, with a slight lean. Let that state hand off into an expanding stage. Once the stage exists, a brief period of rapid stretching may help iron things flatter and push the bumps out to sizes where later processes can't scramble them. When the world cools enough for neutral atoms to form, light decouples and races freely. That light carries the frozen imprint of the bumps as a pattern of slight warmth and coolness across the sky. Over billions of years, gravity amplifies the tiny head starts into the filaments and clusters we see in deep surveys. The early ringing of a hot, light-charged mixture leaves a faint preferred spacing that you can still find in the galaxy statistics. Light from the ancient glow to us is nudged by the mass it passes, leaving a quiet, measurable smear. All of that follows once the handoff lays down simple seeds and the stage appears. What if the seeds weren't simple? If they carried strong preferences for certain sizes, or if the ups and downs were tied together in complicated ways, you would see it in the afterglow immediately. The speckle would not be bland. It would lean and twist in ways that don't wash out. If the seeds were too small or too large, you would fail to get the web we see, or you would produce a web that conflicts with the bend of light we measure. If the beginning favored curves in space too strongly, you would catch that in multiple, independent distance measurements. The advantage of starting from a pre-classical nothing defined this way is that the right mix of smoothness and tiny irregularity is not a wish. It's a requirement built into the handoff. The moment the stage appears with simple seeds, the rest follows with very little room for improvisation. The phrase emergence of time can still feel slippery, so it's worth pinning it down in everyday words. Time isn't a command that the world obeys. It's a way we label change. A ticking clock is just a system that changes in a very regular way, and we use that regularity as a yardstick for other changes. If there's no stage yet, there's no reliable label to use. Once the stage appears, and is smooth and heavy enough. Big picture changes can anchor the label. The overall stretching of the room, the cooling of the background, the steady fading of free electrons as atoms form, the later change in the pace of stretching. Inside that stable context, the label time earns its place. Before that context exists, the label is misplaced. That is all the phrase "time emerges" is claiming. It's tempting to think that we must be missing something dramatic, that surely a beginning should be a firecracker. The sky says otherwise. In all the ways we can measure it, the beginning looks like a handoff that is lawful and quiet, with just enough imperfection to let structure grow. The drama arrives later, as gravity teases tiny leads into galaxies and clusters, and as stars begin to write chemistry across the darkness. The earliest moment the sky can show us is resolutely modest. That modesty is a gift, because it means we can have a simple story that touches a lot of independent facts at once. While we're clearing away unhelpful pictures, it's worth saying plainly that the Big Bang wasn't an explosion in space. There was no center that debris flew from. The distances between points that move with the flow of the universe grew. That's all expansion means here. The handoff gives the stage a rule for how those distances change. The later story is the unfolding of that rule. If you go looking for a central blast site, you'll never find it, because it was never there. There's also the worry that the word probability, when used about beginnings, invites anything-goes storytelling. In a good version of this subject, it doesn't. Probability means you assign weights to different, allowed early configurations, and then you ask what an observer inside the later universe would be likely to see. That only has teeth if the distribution of early configurations is narrow and simple. If your scheme allows almost any pattern with generous weight, you haven't explained anything. You've only shifted the burden. The schemes that survive are the ones where the most weighted beginnings already look a lot like the seed patterns the sky prefers. Another common worry is that all of this rests on ideas, so abstract that any mismatch can be papered over. The right answer is to point at the receipts. The ancient afterglow has been mapped in temperature and in polarization by multiple instruments that disagree about almost everything except the sky. The web of galaxies has been counted by independent surveys using different telescopes and different algorithms. The preferred separation carved by early sound has been measured at multiple distances across cosmic time. The gentle bending of the afterglow and of background galaxies has been extracted by teams that model their cameras and their atmospheres with painstaking care. None of those measurements knows or cares which origin story you like. They only care what pattern they see. If your story can't match all of them with the same seed pattern and the same late-time expansion, it fails. That's not a threat. It's a comfort. It means we're not at the mercy of taste. How much of this is truly universal, and how much belongs only to our visible patch? That question is fair, and it's handled best by the same discipline. If the wider reality is a patchwork in which different regions settle into different habits, so be it. That picture only belongs in a story about our sky if it changes the odds what we should see. If it pushes the seed pattern in a direction, we can check tilting the speckle in a particular way, or sprinkling a gentle beat at the largest scales. Then it earns a place. If it doesn't, it can wait on the shelf without hurting anything. We don't need to decide the whole in order to do honest work on the part we can see. All along, the word lawful has been doing more work than it seems. It doesn't mean fated or inevitable. It means that from a minimal starting description, the rest follows without arbitrary patches. That's the gold standard for an origin story. It's why you can start from no classical stage yet, add the handoff that lays down simple seeds, and end up with a sky that agrees with itself from multiple angles. The fewer special moves you need, the more you should trust the story. When a story starts to collect special moves in different places, just to survive each new measurement, you should set it down. By now, the phrase "from nothing" should be starting to feel smaller in a good way. It's not a grand philosophical claim. It's a very specific translation. No classical stage yet. It's tied to a very specific task. Describe the handoff that turns that regime into a classical world and leaves behind simple seeds. And it's tied to a very specific audit. Check the afterglow, the web, the preferred separations, the bending of light, and the way the expansion has paced itself. If the pieces harmonize, keep the route. If they don't, change the route. That is the whole point of giving nothing a usable meaning. There's room, even in this careful picture, for humility. We haven't said why the rules are what they are, only that they seem stable, and they carry us from the first usable frame to the present without straying. We haven't said which handoff is right, no sharp past edge, a lawful jump, or a rebound only, that each is concrete enough to test. We haven't said that the early world had to look exactly like ours, only that the family of seed patterns it seems to have had is simple and broad enough to make many features of our world stable under small changes. That's enough for now, because it's enough to keep the subject scientific. The last useful thing to carry out of this block is a single compact picture. Imagine holding a tiny, smooth origin in your hand, not a point in space, but a description without classical space or time. Now imagine a switch that brings the stage online. The switch doesn't blast. It whispers. It leaves a faint, random speckle of advantages across scales. The world stretches. Light and charged particles ring together and then let go, freezing in a memory of their beat. Light flies and carries the speckle with it. Gravity amplifies the speckle into the scaffolding of everything you can see in deep surveys. Along the way, the pace of stretching changes in a way we have to fold into every sight line. At no point do you need a miracle. You need a definition, a handoff, and patience. That is what "from nothing" will mean for the rest of this film. Not a conjuring trick, not a slogan, just a workable, testable start. No classical stage yet, a lawful passage that lays down simple seeds, and a sky that still remembers. We've given nothing a workable meaning and said what the first handoff must leave behind. Tiny, simple seeds. Now the sky answers with its own terms. It doesn't argue. It just lays down the rules that any honest origin has to meet. Think of these rules as quiet signatures written into different layers of the universe light, matter, and the way space itself is arranged. If your beginning can't sign its name the same way on every layer, the sky simply says no. Start with the most basic message. The universe is expanding. Not exploding, not throwing debris into an empty room, but the room itself getting larger. Galaxies aren't sprinting away through a fixed arena. The arena is stretching, so the distances between resting points grow. You can see it in the way light from far objects is shifted toward the red, but you don't need the jargon to grasp the point. The stage is changing size. Any origin story that hopes to be taken seriously has to hand off into a world where that stretching is built in. More than that, the stretching can't be wild and uneven. The big picture must be astonishingly uniform, because on the largest scales we can survey, space looks smooth and directionless. Triangles add up the way you expect. There's no obvious bend like the surface of a globe, and no saddle-like warp shouting at you. It's close to flat close enough that you can feel the restraint this puts on the story. If your beginning bakes in a big curve, it won't survive the first step outside. The next message is subtler and lives in the sky's faint afterglow, the baby picture of the universe. It wraps the whole dome like a soft fog of microwaves, almost the same in every direction, but not quite. If you map those tiny differences, you see a speckle that looks nearly scale agnostic. Big patches and small patches carry almost the same level of roughness, with just a gentle lean that favors one side slightly. There's no hidden picture in it, no secret arrows, no preferred direction. And the deviations from perfect randomness are, so far, tiny. That matters. It means the seeds at the handoff were simple in a very specific way. They didn't choose a size to love. They didn't draw a pattern, and they didn't come tangled together with strong built-in relationships. If your beginning makes seeds that are too loud at one size and too quiet at another, the afterglow tells on you immediately. If it weaves the seeds into a complicated tapestry, that shows up too. The baby picture wants modest, almost scale-free bumps with a slight tilt, arranged with near coin flip simplicity. Hit that brief or change your story. While we're looking at the afterglow, there's another layer hiding in plain sight. The light isn't just hotter or cooler, it's also oriented. The directions of those tiny wiggles can be separated into a stretch-like pattern and a swirl-like pattern. The swirl is the delicate one. Part of it is drawn later, when the growing web of matter subtly deflects light and scrambles the original orientation. Part of it could be ancient, left by ripples in space-time itself if the early handoff was very energetic. Getting those two apart is hard work. Dust in our own galaxy can fake the signal. Lensing can imitate it. But the prize is real. A clean, ancient swirl would point back to how punchy that first stage was. If it stays shy even as maps improve, that, too, speaks. Either way, the afterglow is more than a picture. It's a layered record, and a beginning has to pass both layers at once, the speckle and the orientation. The third message arrives not as an image, but as a census. Map galaxies by the millions, and then by the billions, and a pattern comes into focus. A web of filaments with clusters sitting at the crossings and great, quiet voids between. It would be easy to think of that web as decorative, but it's just gravity doing its long, patient work. Where the baby picture ceded a tiny advantage, matter drifted more quickly. Where it ceded a tiny deficit, matter lagged. Over time, the advantages compounded. The details are messy, and local galaxies collide. Gas cools, yet the global statistics are simple. If the seeds had the right, almost even character, the web's texture settles into a predictable form. If the seeds were off, you can feel it out here. The counts of close pairs and wide pairs. The tendency to form certain triangles more often than others. The abundance of the richest clusters, all of it shifts. The web is a slow-motion truth teller. It doesn't care what label you put on the beginning. It only cares what seeds you handed it. Hidden inside that web is a very quiet drumbeat. In the early hot plasma, pressure and gravity set up waves, real sound waves in a medium most of us never think about. When the universe became transparent and the fog thinned, the ringing stopped, freezing a preferred separation into the matter. Billions of years later, the preference is still there, barely, as a faint bump in the chance that two galaxies will sit a certain distance apart. It's not a ruler you can lay across a photograph. It's a nudge you can measure in the statistics. But once you see it, you can use it as a yardstick for the past. When you find the drumbeat at different times, you learn how the room's stretching has paced itself. Your origin story must make room for that beat to exist, must carry it cleanly through the handoff, and must let it survive the long ages of growth. If it can't, the beat says so. There's another way the web holds you accountable, by how it weighs. Light from background sources arrives to us slightly bent by the average pull of everything it passes. The effect is small for any single being, but across millions of galaxies, it adds up to a faint. Statistical shear shapes twisted just a little in the same way. Measure that twist well enough, and you can weigh the web almost independently of how bright anything is. That weight has to match the weight you'd infer if you took the baby. Pitch your seeds and let gravity work on them for 13-something billion years in a room that stretches the way the other clues suggest. If the web looks too heavy for the seeds to explain, or too light for the measured pace of stretching, something is wrong. Maybe with the seeds, maybe with your reading of the pace, maybe with your handling of dust and noise. It's a cross-check that doesn't care about your preferences. The sky set it up that way. The fourth message is a piece of early chemistry and plays the role of a clock. In a hot, dense beginning, certain light elements are forged in fixed ratios, helium, a bit of deuterium, traces of lithium. As the universe expands and cools, the window for that forging closes. Today, when you look in pristine places where later processes haven't muddied the water, those ratios line up with the hot, dense story. The point isn't to add romance. It's to fix the pace. The early chemistry agrees with the baby picture's temperature and with the story of when the fog lifted. It leaves little wiggle room for beginnings that want to change the timing too much. If your handoff is so violent or so sluggish that it wrecks the early clock, the table tips. Then there are the beacons that time the late expansion, certain supernovae that brighten in a way we can calibrate, and other distance markers that give you a ladder to climb. Put those alongside the ruler in the web and the lensing weight, and you get a consistent story of how the stretching has changed. The late stretch is speeding up. That's not an aside. It rebends every line of sight from us back to the baby picture and changes how fast the web can grow. Any origin that survives has to let that be true without causing the other pieces to slip. If the only way you're beginning fits the baby picture is by forcing a late-time story that contradicts the beacons and the ruler, your beginning doesn't actually fit. So those are the sky's big constraints told plainly. The stage is smooth and almost flat. It stretches in a way the beacons and the drumbeat agree on. The baby picture shows tiny, near-scale free bumps with a slight lean and very little hidden structure. The web's texture is what those bumps would grow into. The weight of the web matches the weight you'd expect from the growth, and the early chemistry keeps time with the picture you're painting. None of this requires equations here. It requires holding the shape of the evidence in your head and respecting that shape when you design a beginning. It's also worth speaking directly about how careful people are in extracting those shapes. The baby picture is faint and sits behind the glow of our own galaxy and the murmur of distant dusty sources. To reach it, teams make maps at different frequencies and strip away what doesn't belong. They change the method and see if the result holds. They compare one telescope with another. The map goes from something beautiful to something reliable by surviving those changes. The web is measured by counting galaxies in catalogs that are themselves full of biases. What you can see depends on how bright and how far, and on how the survey was stitched together. So teams simulate those biases and push their counting methods through fake skies to understand their own habits. The lensing signal is tiny and easily confused with distortions from lenses that aren't cosmic at all glass in the camera. Air above the telescope, so the modeling gets painfully detailed. Each time an analysis path is changed and the same answers survive, confidence rises. It isn't glamorous, but it's why the constraints mean anything. They've been scrubbed of the most obvious ways to fool ourselves. Even after all that care, the sky keeps a few quirks that people argue about at the edges. On the very largest scales in the baby picture, power seems a little low compared with the simple seed story. There are debates about whether a certain cool spot is a real oddity or a statistical fluke dressed up by our love of patterns. Some distance measurements of the recent stretch have disagreed in detail with what you might infer from the baby picture alone, prompting hard looks at both sides' assumptions. This isn't scandal. It's how a living subject behaves. The right attitude is simple. Catalog the quirks, check them against new data, and see whether they hold up as the instruments and the methods improve. If they do, they'll push weight from some beginnings to others. If they don't, they'll fade without ceremony. Either outcome improves the map. What do these constraints ask of a beginning in practice? First, smoothness that is not perfection. You need a world that is almost uniform and almost flat at handoff, but not so sterile that nothing can grow. Second, seeds that are simple in a statistical sense. No favorite directions, almost the same roughness across a wide range of sizes, and no hidden ties that would leave a complicated fingerprint on the baby picture. Third, timing that's compatible with the early chemistry and with the moment when light first ran free. Fourth, a way to carry the seeds forward without smearing them. The little bumps must survive the early, bright ages in a way that leaves their imprint on the afterglow and still gives gravity something to build with later. Fifth, peace with the late-time story. Whatever made the handoff happen can't force a late stretch that breaks what the beacons and the rulers say. There is, tucked under all of this, a lesson about how broad a success can be without being empty. Nearly scale-free bumps sounds vague until you realize how tightly the afterglow pins it down. Almost flat sounds forgiving until you try to bend space and keep the beacons and the drumbeat in tune. Nearly random sounds like a shrug until small correlations that shouldn't be there leap out of the baby picture. It's like drawing a line through 5 points with one curve. You can wiggle the thickness a little, but the path is set. The sky lets you be simple, not sloppy. There's another quiet constraint that doesn't get as much attention because it's about what isn't there. The baby picture is so clean that it leaves very little room for dramatic departures from familiar physics in the early hot plasma. If you try to add wild interactions or exotic behaviors that tangle the seeds after handoff, the picture balks. The ringing that writes the ruler into the web is very sensitive to extra ingredients that change how tightly the plasma is coupled. And the silence of big departures is itself a verdict. Whatever your favorite spice is, you have to use it sparingly. The stew is already good. One of the strongest upsides of using the sky this way is that it reduces the feeling of arbitrariness in picking between beginnings. You don't have to love the aesthetics of a no-past-edge handoff to keep it on the table. You only have to admit that it produces seeds in the right family and passes the layered tests. You don't have to reject a lawful jump from a non-classical state because it sounds too bold. You only have to see whether the odds it assigns to seed patterns bias the afterglow in a way that's allowed. You don't have to embrace a rebound for philosophical reasons. You only have to see whether the biggest scales in the baby picture carry the quiet beats some rebound versions predict, and whether those beats persist under scrutiny. The constraints serve as a referee that doesn't care who's in the ring. Now, a word about the feeling that all of this is too statistical to be real. It's true. The strongest claims here are about patterns, not singular events. But that's the right scale for a universe that gives you exactly one sky to work with. You can't reset and replay. What you can do is measure many independent pieces of that one sky and ask whether a single simple seed story explains all of them at once. That kind of explanation is every bit as real as the weight of a stone or the note of a bell. It just speaks in averages and variances rather than in bangs and flashes. There is also a fair concern that we're reading too much into smoothness. Isn't a neat beginning improbable? Yes, if you count without context. It's rarer to be smooth than to be messy. But if the only doorway to a universe that looks like ours is a neat beginning with tiny bumps laid down by lawful rules, then improbable stops being a reason to object and turns into a description of what was required. You don't choose it because it's pretty. You accept it because it's the only route that prints the same signature on every page of the ledger. Finally, it's worth drawing the threads together, the way you might in a control room before pressing record. We have a stage that stretches and is almost flat. We have a baby picture with simple speckle, a slight tilt, and no secret directions. We have a web that grew from those seeds and carries a faint drumbeat from a time when light and matter rang together. We have the weight of the web measured by the way it bends light. We have an early chemistry that times the heat and density. And we have a late stretch that speeds up and must be included in every line drawn from us back to the beginning. That full set is the shape of the sky's rules. Not one of them, not two of them, all of them at once. From here on, whenever we talk about a specific path to the first classical frame smoothing without a sharp past edge, a lawful jump into expansion, or a rebound through a careful contraction, these are the terms of the deal. The path has to produce the right family of seeds, deliver them cleanly to the baby picture, let them grow into the web at the right pace. Respect the early clock and the late acceleration, and keep the weight of the web and the bend of light in step. If a path can do that without clutching a bag of exceptions, it stays. If it can't, the sky politely shows it out. That's the comfort of using constraints rather than slogans. You aren't leaning on taste. You're watching for the same quiet signature in 4 or 5 different languages: temperature, orientation, positions, weights, and distances. If the signature matches, you're looking at a real story about the world. If it doesn't, you're looking at a sentence that just sounds good. From nothing to now, this is the audit trail. And the best thing about an audit trail is that it's patient. It will still be here when we come back with sharper maps and better cameras. The rules won't change, only our ability to read them will. So we have our guardrails. They aren't loud, but they're firm. Any beginning we consider next will be asked the same questions and graded the same way. The sky doesn't play favorites. It just keeps excellent records. We talk about time like it's the air. Always there, always flowing, always counting. But nothing in the sky's record says that time had to be part of the very first description. What the evidence supports is quieter, and in a way, more satisfying. The earliest usable picture of the universe doesn't need a ticking clock. Time becomes a good word only after a certain kind of order appears, after there's a stable background to measure change against. Before that, before and after aren't wrong. They're just the wrong tools. Think about what a clock really is. Strip away the face and hands, the beeps and buzzers, and you're left with a device that repeats. A pendulum swings, an atom flips, a crystal hums. Something cycles in a dependable way, and we use that rhythm to label other changes. The rhythm isn't magic. It's a property of a system in a stable setting. Stretch that setting too fast, shake it too hard, and the rhythm loses meaning. In the earliest regime of our story, the one we've agreed to call pre-classical, there is no stable stage yet. The very idea of a room to swing a pendulum in is missing. There can be rules, and there can be structure, but they aren't written in the coordinates we use once the stage is up. So time, as a label we can build clocks for, simply hasn't switched on. When the handoff occurs, when the description of the world becomes classical in the large, when the room is there, then clocks come alive. You don't have to build one to know it. The whole universe becomes its own clock. The background is smooth and heavy enough that its changes are slow and coherent. Distances between points that drift with the flow increase in step. The mix of ingredients cools in a steady way. A fog of free electrons thins until atoms take hold. Later, the overall pace of stretching itself changes. Each of those is a dependable rhythm. From this point on, using the word time is not only allowed, it's useful. This isn't philosophy for its own sake. It matters because it clears room for an origin story that doesn't pretend there was a moment before the first moment. The handoff we keep talking about is a lawful relation between a regime where time isn't yet a good coordinate and the regime where it is. Once you accept that, you stop asking questions that tie themselves into knots. You don't need to list a cause for the handoff in the everyday sense of an earlier push. You need to show that the handoff is consistent, that it leaves behind the simple seed pattern the sky prefers, and that from that point forward, the universe keeps perfect minutes by its own rhythms. That's what the evidence shows. Now, what about the direction of time, the way everything seems to run from simple to messy, from neat to jumbled, from concentrated to spread out? That arrow is the one you feel when a hot drink cools and never spontaneously warms, when perfume diffuses and never climbs back into the bottle, when a stack of papers can topple but never leaps into order. You can say entropy to name it, but the word doesn't add magic. It only labels the count. There are more ways to be jumbled than to be tidy. The arrow you live inside is the tug toward the larger set of arrangements. On small scales, the forces that move atoms around don't have a built-in direction. Run the equations backward, and they look just as legal. The reason you don't see the backward running is census, not law. If you start from a tidy beginning, the next states that are still tidy are a sliver. The next states that are a bit more jumbled are a whole country. Left alone, systems wander into the country, not the sliver. They do that because there are countless paths into the mix and almost none into the stack. The universe applies the same logic on beautiful, enormous scales. The handoff leaves a beginning that is extraordinarily smooth. That smoothness isn't nothing. It's the reason the arrow points the way it does. In a smooth mass distribution, gravity hasn't had its fun yet. There's room to grow structure room for tiny advantages to turn into galaxies and filaments, for clouds to cool and form stars, for stars to cook heavier elements, for planets and chemistry to become interesting. Smoothness at the start is low gravitational disorder. Clumping increases the number of ways matter and light can be arranged. A black hole in extreme clump is the ultimate example of that increase, carrying a disorder count that dwarfs everything else. So as the universe ages from smooth to clumped, the arrow you feel in your kitchen is echoed by the arrow written across the sky. This is the part that can feel counterintuitive if you're used to thinking of order as symmetry. The early universe looks ordered to us because it's the same everywhere. Nearly uniform, nearly flat, no favorite directions. But from gravity's point of view, that is the tidy stack. There are very few ways to distribute matter so evenly across such a vast volume. The moment you allow small bumps, the options explode. Let gravity amplify those bumps, and the options keep expanding. The pretty symmetry of the same everywhere is special not because it's beautiful, but because it's rare. That's the sense in which the universe starts in a low disorder state, even though it looks so simple. You can check this with the sky's receipts, and you don't need a single formula to do it. The baby picture, the faint afterglow of the hot young universe, is a near-perfect uniform wash with a fine speckle. That uniformity and that speckle together tell you that the beginning was unusually smooth, with tiny, simple irregularities. The later maps of galaxy positions show a foam that is anything but uniform. Filaments and clusters surround broad emptiness, a picture of gravity at work, making the world less tidy in the specific, countable sense. The subtle bending of light that reaches us from behind those structures tells you that the mass has indeed moved. The pattern of that bending agrees with what you'd expect if small advantages had a few billion years to bloom. Each layer of evidence points in the same direction, from smoothness with tiny seeds to complexity that blossoms under gravity. The arrow is as real as any direction can be. There's a lingering worry that people sometimes press here. If the fundamental rules don't have a direction, isn't the arrow an illusion? No, it's a property of the initial condition. Call it special if you like. Call it finely tuned if you want to emphasize that there were far more messy possibilities than neat ones. But don't call it an illusion. The receipts are sitting in plain view. What the discussion of arrows does, when it's done honestly, is move the weight of explanation. You can't explain the arrow with a new force. You explain it with the start. A low disorder beginning and ordinary evolution under gravity are enough. Another way the arrow shows up is in the very existence of classical behavior. The pre-classical regime is a world where the right language isn't. Here's a definite value for this, but here's a range of allowed options and how they hang together. After the handoff, that language changes. We talk about galaxies sitting in specific places, about stars having definite temperatures, about atoms emitting light of certain colors at certain times. The bridge between those two ways of talking is something that happens because the universe is big and full of interactions. Delicate phases that tie options together become spread out into countless environmental details. You don't track those details. No one can. The result is that the world behaves like it has definite properties in the large. That process has a direction too. It's much easier to lose delicate coordination than to assemble it spontaneously. more ways to smear than to tighten. The same census that gives you the thermodynamic arrow gives you the arrow from fuzz to fact. None of this requires putting a special glow on the handoff. The passage isn't a firecracker. It's a change of description that becomes stable once the stage exists. Beforehand, the rules don't mention a clock. Afterward, the rules are read in a setting that supplies regular changes. And the arrow of time, our reliable sense that the film runs one way, comes not from a secret in the equations, but from the unusual simplicity of the early state. The universe didn't begin perfectly. It began simple enough to make complexity likely. It helps to walk through a few landmarks with this in mind, because the arrow is hiding in each one. Take the moment when the fog lifts and the universe becomes transparent. Before that moment, light ricochets off free electrons and can't carry a clean picture of anything. Afterward, light flies and the afterglow forms. The change sticks because the conditions keep drifting the same way. The room keeps stretching. The average energy per particle keeps dropping. The fog doesn't return. There are many ways for the fog to thin and stay thin. There are almost none for it to spontaneously thicken and erase the afterglow. The direction of first the fog, then the photograph, is the arrow again. Move forward to the time when the first stars light up. Those stars are only possible because gravity had time to turn tiny differences into real density contrasts. Because gas could cool enough to collapse. Because heavier elements weren't needed yet for the first round of ignition. That whole cascade depends on starting from smoothness with small seeds. If you started from turmoil, huge wild swings built in, you'd choke star formation or make something so different that our later maps wouldn't exist in their present form. The arrow from simple to structured is even baked into the night sky we see when we step outside. A past that was more even, a present that is textured. Look at the thin, whisper-faint rhythm that survived from the early days, the preferred spacing among galaxies that plays the role of a ruler. That rhythm is a fossil from a time when a hot mixture rang like a drum. The drum stops when the fog lifts. The rhythm stays. As the universe ages and the web thickens, that preferred spacing becomes harder to hear, but it doesn't disappear. The fact that we can still find it means that the path from ringing to quiet didn't take a sudden detour back to noise. It went the way the arrow points, from an early symmetric behavior to later, broken symmetry with lasting traces. Again, many ways to keep the trace, precious few to reverse it. There's a late-time piece of the arrow too, and it lives in the pace of stretching. Today the expansion speeds up on the largest scales. That change in pace is part of the clock the universe keeps. You can see its marks in multiple kinds of data at once. A gentle change in the photograph's statistics, a shift in how the ruler appears at different distances, a pattern in the catalogs of supernovae that serve as reliable beacons. This late-time behavior doesn't erase the earlier arrow. It sits on top of it. Light that left the afterglow has to cross a landscape that's been changing its stretch rate, and the details of that crossing get written into the patterns we measure. The direction of the story remains the same, no rewinding, no erasing, just a new chapter with its own steady beat. Why spend so much care on such a simple idea? Because people often smuggle in a different story without noticing. That the arrow is a kind of cosmic command, that there's a force with a name like time's push, that we haven't explained anything until we name that force. There is no extra push. There is a start so spare that moving away from it is overwhelmingly likely. There are rules that don't care which way you label future and past, and a reality that does because it began in a special arrangement. That combination is not a dodge. It's the honest heart of the thing. You might ask whether alternative paths to the first classical frame change this account of the arrow. Do they? Not in the broad strokes. If the earliest region is smooth and regular, with no sharp edge in the past, the arrow follows from that regularity. It selects the neat stack over the scattered pile. If the earliest region is a lawful jump into expansion, from a non-classical catalog of options. The arrow follows from which options carry the most weight, the ones that look like the simple seed family we read in the sky. If the earliest region follows a careful contraction and a rebound, the arrow still depends on making the state after the turn smooth enough that growth is possible and disorder can rise. In each case, the arrow is set by how special the post-handoff state is, not by the label on the route you used to get there. There is a slightly different worry that pops up around this point. If the arrow is tied to a low disorder start, aren't we just explaining one mystery with another? Only if you think the job of physics is to remove all special features from reality. It isn't. The job is to connect special features to measurable consequences and to show that they are necessary. The smoothness of the start isn't an ornament. It's a requirement. Try to do without it, and you can't get the sky's 5 receipts to agree. The fact that the world actually did begin this way is not something we choose because we like simple stories. It's something we read off the map the sky gives us. And the map doesn't just tell you what the arrow is. It tells you how time became a useful label in the first place. When the handoff produced a smooth background, all the clocks were born at once. The overall expansion, the cooling, the thinning of fog, the first stable atoms, the first starlight. Those clocks let other clocks be built. You can trace that cascade in the evidence. The afterglow pins down when the fog lifted. The abundance of light elements pins down how hot and dense things were when the universe acted like a nuclear furnace. The pattern of galaxy clustering pins down how quickly structure could grow. The lensing maps pin down how much matter the light crossed on its way to us. The late-time beacons pin down how the pace of stretching changed after most of the web was in place. Put them together, and you have a timeline that wasn't imposed by us. It was offered in polite detail by the universe. This approach also makes sense of something that can sound like a riddle. If time emerges, how can anything happen before it? The answer is that you don't need a before in the ordinary sense. You need a relation between two descriptions. One description doesn't include a coordinate called time because the stage isn't there. The other description does because the stage is there. The relation that links them isn't a story of an event preceded by another event. It's a lawful connection between two levels of description. That's enough to get a universe you can recognize and a sky you can read. You can carry this thinking down to smaller scales without breaking it. In a lab, the difference between a quantum system that acts fuzzy and one that behaves classically is often how much of its environment it's entangled with. Isolated, it keeps all its delicate options alive. Bump it into enough surroundings, and those options become spread into details you can't track. The result is classical behavior. The early universe is the ultimate environment. There's nowhere outside of it. As the stage appears and the number of degrees of freedom grows, the delicate early possibilities are recorded in countless quiet ways that no one is keeping a ledger of. The result is that the large-scale degrees of freedom behave classically. That transformation is not a bolt of lightning. It's a drift from possibility into history. And because there are many ways to smear options and very few to recollect them, this drift has a direction too. If you like, you can look for the arrow in light itself. The afterglow started out with a temperature that was almost the same in all directions, and with a pattern of tiny differences that we can map. As the universe grew larger and cooler, the average energy of those photons dropped, and their distribution changed in a way that we can measure precisely. That change is one way. There's no plausible path in which an enormous volume of space that's already transparent and sparsely populated suddenly conspires to bring that light back to its earlier state with the right tiny wiggles restored. Not because it's forbidden by the rules, but because there are vanishingly few arrangements that would make it happen. Again, the census, not a command, sets the direction. This way of talking about time is, at bottom, a relief. It takes a word we use constantly and makes it honest. We don't need to imagine time as a river that was flowing before the universe had banks. We don't need to mystify it as a primitive ingredient that was present even when nothing else was. We can treat it as a label that becomes valid when there's something regular to label, and we can treat its direction as a legacy of the overwhelmingly simple start the sky points too. That's not poetry. That's a practical way to make the headline question answerable. There's a final piece that belongs here because it keeps your head clear for the next chapters. When we move on to specific routes to the first classical frame smoothing with no sharp edge, a lawful jump into expansion, a rebound after careful contraction, none of them gets to choose its own arrow. The arrow is non-negotiable. Each route must produce a state that is smooth enough, simple enough, and stable enough that the rest of the universe's history can proceed from neat to messy, from uniform to structured, in the measured way the receipts describe. If a route cannot produce that state without hidden fine-tuning everywhere, the sky will let us know. If it can, the arrow will carry forward automatically. So time, in this story, is not a character with a personality. It's a habit the universe can afford once the stage exists. Its arrow is not a law with a badge. It's a reflection of how rare the beginning was and how many paths led away from it. We don't need to make it more dramatic than that. The drama is in the reach. That a quiet handoff with tiny, simple seeds can determine how clocks are born, how the photograph is taken, how structure grows, and how the late time stretch reshapes every line of sight back to the start. The nice thing about this view is that it scales all the way back to you. The arrow you feel when you clean a room and it won't stay tidy, when you open a bottle and the scent won't walk back in, when you watch a hot drink cool, isn't separate from the arrow that allowed stars to form and galaxies to web together. It's the same tilt in the census, written at human size. The universe didn't invent an extra rule for your kitchen. It gave you one set of starting conditions and one way they like to unfold. That's the backbone we need before we talk details about the first stage. We know what time is doing and why it runs the way it does. We know when it becomes worth talking about and why talk of before can be a mismatch near the handoff. We know that the arrow is not mysterious once you admit the specialness of the start. With that in our pocket, we can turn to the different ways the handoff might have happened and keep our bearings. However, the switch was thrown smoothly, without a sharp past edge, by a lawful jump, or by a rebound. The sky will ask the same questions of each, and the clock we've just understood will keep on ticking the only way it can, from simple to full, from plain to elaborate, from the neat stack to the scattered pages of a living cosmos. If the early universe was handed a simple set of tiny bumps, the seeds, we've been talking about something still had to make the big picture look as even as it does. That something is what people call inflation. Strip the word of mystery. Inflation is just a very brief phase in which space expanded much faster than it does now. So fast that any leftover wrinkles were ironed flat, and any clutter was pushed out of view. It didn't conjure the universe. It didn't flip a switch on time. It acted more like a smoothing pass at the start of the classical stage, and its job was practical. Make the stage wide, level, and quiet enough that the later story could unfold without constant surprises. Why would such a phase help? Imagine you're trying to paint a wall. If the plaster underneath is lumpy, the light will catch every flaw, no matter how carefully you roll the paint. Inflation is the skim coat. It doesn't add color. It evens the surface. In cosmic terms, rapid, almost steady expansion blows away leftover curvature, spreads out any local mess, and leaves our visible patch looking astonishingly uniform. At the same time, it takes the tiny seed bumps that the handoff provided and stretches them to enormous scales, freezing them in place so later processes can't easily scramble them. When the baby picture was taken, the afterglow, we can still see that stretched pattern was already there. The useful twist is that inflation isn't only a cleanup crew. It also writes the seeds into a form that the sky recognizes as simple. When a region expands that quickly, The sizes of the bumps that cross a certain threshold do so in an orderly way, and their strengths end up very similar across a huge range, with only a small lean. That's exactly what the afterglow speckle looks like. Almost the same roughness at many sizes, gently tilted with no hidden directions or angles. This match between what a smoothing phase naturally produces and what the sky actually shows is the core reason inflation became the standard language for the first moments of the classical stage. It wasn't adopted because people wanted fireworks. It was adopted because it lined up with the data in calm, repeatable ways. But there's something easy to get wrong, and it's important to say it clearly. Inflation is not a mechanism that makes a universe from scratch. It doesn't answer why anything at all, and it doesn't replace the need for a lawful handoff from the pre-classical regime. It assumes the handoff has already happened, or is being described in some lawful way, and then it describes what the first classical moments do: smooth, stretch, and set the seeds into a readable pattern. If you treat it as a creation story, you'll ask it to do a job it was never designed for and call it a failure for the wrong reason. If you treat it as a smoothing engine, you can judge it on what it actually claims. What, then, would make inflation a good citizen of the bigger story? First, it should start naturally enough that you don't need to stack special conditions on top of special conditions. Second, it should end gracefully and hand the universe its heat and particles. Since the world soon after the baby picture was a hot plasma in which light was constantly bouncing off charged particles. Third, it should predict a seed pattern that looks like the one we actually measure, nearly scale independent, slightly tilted, nearly random, with no hard-to-explain structure. Fourth, it should get along with the late-time pace of stretching. The path from the afterglow to us goes through billions of years in which the expansion changes gear, and inflation's job is to deliver initial conditions that evolve cleanly through that. Finally, it should make at least one prediction that can, in principle, fail a place where the sky can say no. The ending of inflation has a simple name in the field: reheating. Don't be distracted by the label. It just means that whatever drove the rapid smoothing handed its stored energy over to the ordinary stuff that later filled space photons, neutrinos, the particles that would become the raw material for atoms. The temperature rose, not to an infinite degree, but to a level that matched the hot, dense conditions we infer from the early chemistry of light elements. That transfer of energy is part of why inflation is a useful bridge. It leaves the world not empty and cold, but busy and bright, with the right ingredients to form the fog that later thinned into the afterglow. There's a practical backbone behind the talk of stored energy. During inflation, the effective energy density that drives the expansion changes, very slowly compared to the rate at which space itself is stretching. The rule for the stretch is roughly double and double again, on timescales that are short compared with anything afterward in cosmic history. Because the driver isn't draining quickly while that happens, the expansion stays almost steady while it irons the stage. The specifics vary from model to model, and there are many, but the shared feature is the near steadiness of the engine during the smoothing pass. When the engine finally lets go, the stored energy doesn't vanish. It becomes the heat of the young universe. If you want to understand why the afterglow cares so much about whether such a phase happened, imagine a patchwork quilt where each square is its own tiny weather report. Without inflation, you'd expect different squares regions that are too far apart to have communicated before the photograph was taken, to look unrelated. But the afterglow is surprisingly uniform across such huge separations that too far apart becomes a puzzle. Inflation solves it simply. Before the photograph, the squares were closer together. The fast smoothing phase made them far apart after they had time to settle into the same temperature. No drama, just extra room created early, so uniformity makes sense. Another friction inflation relieves is geometric. A universe that begins with any leftover bend curvature would keep that bend as a noticeable feature unless something pushed it down. Inflation pushes it down. In an expanding world, then it's diluted, just like any other irregularity. Push enough, and space looks flat over the patch we can see. The fact that our sky is so close to flat triangles add up the way they do in school, with almost no detectable deviation, is an everyday way of saying that this dilution likely happened. The seed pattern that inflation naturally writes carries 3 quiet signatures that the afterglow and the later Webb can check. The first is the near equality of roughness across sizes, the almost scale-free character of the speckle, with a slight tilt. The second is the plainness of the randomness, bumps and dips that behave like independent coin flips once you've accounted for the way gravity later grows them. The third is a potential whisper of space-time ripples from the early smoothing phase, a tiny, swirl-like pattern in the orientation of the afterglow's light. That swirl is the hardest to measure cleanly because later bending by the Webb and dust in our own galaxy can imitate it. But if it were seen at a certain strength and across a certain range of sizes, it would be a direct message from the smoothing engine itself. If it keeps refusing to show up as measurements improve, it trims away the more energetic versions of inflation while leaving gentler versions standing. There's a version of this story that goes further and says the smoothing phase, once started, is very hard to turn off everywhere at once. In that picture, some regions switch out of inflation and go on to make stars and galaxies, while others keep smoothing. The whole becomes a patchwork that we can't survey in full because of horizons. Those are simply limits on what can have sent us signals since the baby picture. As we already promised earlier, we keep this in the background unless it changes the odds for what we should see here. Sometimes it does, by affecting which seed patterns are likely in a region like ours. If it doesn't, we don't need it to make contact with the data in our patch. No honest account would skip the criticisms inflation has faced. One line of worry is that it seems to require some luck to start, that the engine has to be in the right condition over a large enough region to take off. Another is that with too much freedom in the details, inflation can be made to fit almost anything, which makes it less predictive. A third is that in the patchwork version, making sense of typical becomes hard. How do you weight all the patches when you can't count them properly? These are real concerns. The way they've been handled, at least in the part of the subject where data rules, is by preference for versions of inflation that are robust. Robust here means they deliver the simple seed pattern with minimal delicate setup. They end and reheat cleanly, and they don't depend on a sprawling menu of adjustable ingredients to survive each new measurement. This preference shows up in how people talk about how simple is simple. If a smoothing model can match the afterglow and the Webb with a small number of stable assumptions, it stays. If it needs special shaping to mute or enhance particular sizes in the speckle, it becomes suspect. If it predicts large, distinctive deviations from the near coin flip randomness, and those deviations aren't seen, it is retired. If it says the swirl-like pattern in the afterglow should be strong across a wide range of sizes, and the best cleaned maps keep saying, we don't see it, then the more energetic takes get sidelined. The upshot isn't that inflation is unfalsifiable. It's that the family of inflationary stories that work has been steadily trimmed by exactly the kind of receipts we've been talking about. There's a second family of inflation stories where more than one ingredient participates in the smoothing. Think of it as a team effort during the early pass. The effect on the sky can be subtle. Small departures from coin flip randomness, or gentle preferences that look like tiny beats across certain scales, or a whisper of extra flavors of sea bumps that don't track the density of matter in lockstep. These variations are interesting because they're testable. If the afterglow and the Webb keep saying as simple as you can make it, with no extra flavors allowed, then team effort models get narrowed. If delicate allowed departures appear consistently, they'll point back to teams and away from the solo act. So far, the sky has been conservative. It keeps preferring plain seeds. That preference isn't proof that only the solo act is right. It's a limit that any team version has to respect. What about the energy scale of the smoothing? People sometimes imagine inflation as a kind of all-or-nothing blast. In reality, the how energetic question is exactly the kind that the afterglow's polarization pattern can answer. A strong early smoothing would have sent more powerful ripples into spacetime. A gentle smoothing would have sent fewer. Each case leaves its own signature in that delicate swirl. Once you've peeled away the lensing that later structure creates, and the dust that our own galaxy adds, the fact that we haven't seen a crisp, ancient swirl yet doesn't kill inflation. It trims the space of models that inflate hotter. The tightening of those trims is the kind of progress you want, narrowing what's allowed without having to change the framework every year. If you want to see where inflation earns its keep most, keep your eye on the way it lets one story explain several independent facts with the same handful of sentences. The afterglow's near-uniform speckle? Natural. The slight tilt? Expected. The lack of strong hidden structures? Built in. The near-flat geometry of space? A direct result of smoothing. The presence of that faint ruler in the galaxy distribution? Compatible with how the universe behaves once smoothing hands off to a hot plasma. The optional swirl pattern in the afterglow's light? A bonus prediction whose absence so far narrows the high-energy end. One engine, several pages of the ledger addressed. That's what explanation looks like in a field that lives on patterns, not big revelations. There are limits to how far a single engine can go. Inflation won't tell you why the rules are the rules. It won't tell you whether the pre-classical regime is best described as no past edge, a lawful jump, or a rebound. It won't settle whether the wider reality is patchwork. It won't guarantee that the swirling pattern is exactly at this strength, only that a range is expected. But it will give you a waypoint, a brief stage of rapid smoothing at the start of the classical era that naturally sets the seeds in the form the sky prefers and that hands off to a hot, dense world at the right time. In that sense, inflation is like a lens. If it's the right lens, your picture comes into focus across several frames at once. A fair question is how inflation could be wrong in a decisive way. One path would be if the afterglow showed a strong, repeatable structure in its speckle, a loud preference for certain sizes or strong ties between ups and downs that plane smoothing does not produce. Another path would be if the universe's geometry turned out to be measurably curved in a consistent way across several methods, beyond what smoothing can plausibly dilute. A third would be a robust detection of a swirl pattern of the wrong character, one that doesn't look like the imprint of early spacetime ripples, but like something harder to square with the smoothing pass. A fourth would be a consistent set of measurements showing that the faint ruler in the galaxy distribution sits in the wrong place, once you account for the expansion story that the afterglow and supernova prefer. None of those would kill the idea that there was a smoothing pass. They would kill particular implementations. Kill enough, and the whole picture would have to be replaced by something that does the same jobs better. There is also an indirect wrong that matters. If a different route to the first classical frame, say, a careful contraction followed by a rebound, can explain the afterglow's speckle, the near-flat geometry, the ruler, the web's growth, and the absence or presence of the swirl pattern with fewer assumptions and fewer moving parts, then the balance of attention naturally shifts. This is not about loyalty to a label. It's about economy. The winning story is the one that accounts for the most facts with the least special pleading. Since we're trimming jargon wherever we can, it's worth laying out the everyday consequences of inflation as you'd actually meet them in pictures and plots. You'd see the afterglow map mostly uniform, sprinkled with tiny variations match a simple curve across sizes with a slight lean. You'd see the orientation of that light broken down into stretch and swirl, with the swirl cleaned of dust and later bending, and you'd either see it whispering at a level consistent with gentle smoothing or not see it at all within the new limits. You'd see a plot where pairs of galaxies are a tiny bit more likely to sit at one particular separation, then at nearby ones the ruler showing up at different cosmic times in a way that traces the expansion. You'd see the plot of distance versus dimness for standard explosions. Draw a line that shows late time speeding up. And you'd see lensing maps, which are really shape maps, reflect the weight of the web in a way that agrees with what the seeds would have grown into by now. Inflation is just the short name for a stage that makes these pictures hang together. One day, a crisp detection of the ancient swirl may arrive, or a gentle, broad deviation from perfect coin flip seed randomness may be confirmed in a way that points to extra ingredients at the smoothing stage. Or new, full sky maps of the web's weight may nudge the late time expansion story and require adjustments to the seed amplitude. Each of those would sharpen the situation. If the swirl shows up at a level that gentle inflation allows, great, you've filled in a missing square. If it shows up too strong to be reconciled with our web and our afterglow in the same breath, something larger has to give. If no swirl keeps showing up under ever better cleaning, then the high energy versions lose weight and the lower energy ones gain it. If the web's weight and the afterglow seeds keep matching under the same late time expansion story, you've stress tested the chain. The point is that inflation's fate isn't tied to taste. It's tied to receipts. Zooming out, there's a calmer, more general truth hiding here. Early rapid smoothing is a way to build a universe that can age well. A world that begins too jagged never settles into the quiet uniformity we read in the afterglow, and it never lets gravity do its long, patient work without constant interference from leftover mess. A world that begins perfectly smooth never grows anything at all. A world that begins smooth with tiny, simple bumps and then smooths those bumps into the form the sky prefers has a clean path forward. That path is the reason we can turn the headline question into a map. Not just how could a universe begin, but how do you begin a universe that looks like this one? If you want one sentence to carry forward from this section, let it be plain. Inflation is an early, brief smoothing phase at the start of the classical era. It doesn't make a universe. It prepares one. It levels the stage, sets the seeds into a simple pattern, and hands the world off hot and busy. It earned its place not because it sounds exciting, but because it explains quiet facts in many places at once. The evenness of the baby picture, the slight tilt of the speckle, the near flatness of space, the presence of a faint ruler in galaxy statistics, and a potential, very faint swirl in the ancient light. Where those facts tighten, inflation narrows. Where they shift, inflation shifts or gives way. Either outcome is science doing what it's supposed to do. Hold on to that tone as we move to the next roots. We'll look at a beginning with no sharp past edge, where the early region is regular and compact, and time only becomes a useful word as the stage appears. We'll look at a lawful jump from a non-classical state into an expanding one, where the simplest expanding configurations are more likely than Baroque ones. We'll look at a careful contraction and a rebound, where wrinkles are ironed out before the turn, and tiny beats might remain at the largest scales. Each root will be held to the same standard. Seed simple enough, handoff clean enough, and the whole ledger from afterglow to web, to ruler, to lensing to late expansion, brought into the same quiet agreement. A good origin story should not lean on a hidden wall it can't describe. The attraction of the no-boundary idea is exactly that. It removes the wall. Instead of a first instant that demands a what came before, the earliest region is smooth and regular, a compact cap in which our usual labels space here. Time there haven't separated yet. There is no edge to ask about. The useful words only switch on once the stage enlarges, and the difference between duration and distance becomes a stable feature of the world. That's what no boundary means in plain language. Not that there was a magical void, but that the first usable description has no past rim you could put your finger on. The picture is less strange when you talk about what the sky needs from any beginning. It needs a handoff that produces a classical stage ordinary space and time. together with a simple pattern of tiny irregularities. It needs that handoff to be lawful, not a shrug. It needs the irregularities to be simple enough that later processes can carry them forward without inventing structure that doesn't exist. And it needs all of that to agree with the receipts we can read, a nearly uniform afterglow with a gentle lean across sizes, a large-scale geometry that is very close to flat, a faint ruler frozen into the distribution of galaxies, light that arrives to us slightly bent in the right way, and a late-time expansion that changes pace without breaking the rest. The no-boundary idea is one clean way to meet those needs. Start from the core claim and keep it literal. The earliest region is regular and compact. There is no meaningful earlier within the description. The labels before and after do not apply because the coordinate that later becomes time has not taken on that role yet. The rules at that stage are real, but they are not written in the language of a clock. From that regular cap, the description continues smoothly into the classical stage. As it does, the distinction between time and space appears, because the world now has a stable background that supports the label change per unit duration. In that passage, tiny irregularities are laid down. They are simple by construction, nearly the same strength across a wide range of sizes, arranged without a secret picture or a favorite direction, with only a mild tilt that later observations can measure. That is the content stripped of slogans. It helps to state what this does not require. It doesn't require an explosion. The distances between points that drift with the flow begin to grow. That is all expansion needs to mean. It doesn't require a singular break where equations fail. The point is to use a description that never demands such a break. It doesn't require a moment zero you can put on a calendar. The earliest region is more like a smooth dome you can stand on than a cliff edge you can fall off. If you insist on asking for a time coordinate all the way down, you're using the wrong tool for that part of the job. Why would such a beginning be attractive beyond philosophy? Because it naturally picks out smoothness. A no-boundary regularity condition says, in effect, don't allow jagged starts. It restricts the earliest region to configurations that are well-behaved everywhere. When the classical stage appears, that restriction shows up as an initial state that is extremely even, with tiny deviations sprinkled in a statistically plain way. From then on, gravity and ordinary processes take over. The seeds are already what they need to be. The later pictures, the afterglow, the web, the ruler, the lensing are what you would expect if you began from such evenness. The afterglow, in particular, reads this start like a book. A no-boundary beginning leans toward seed patterns that are close to scale independent, with a gentle tilt. It does not favor a hidden direction. It does not draw a grid. It does not produce strong built-in ties between ups and downs beyond what ordinary growth will add. Those features match what the afterglow maps show. A soft speckle with no secret arrows, and a mild preference that larger patches carry just a little more roughness than smaller ones. If you had started with a pattern that loved one size too much, the speckle would give you away. If you had started with complicated ties, the statistics would be skewed. The no-boundary way of starting avoids both traps by design. There is also an optional signature that's delicate to read, the tiny swirl in the orientation of the afterglow's light. A no-boundary beginning can live happily with versions of the early classical stage that are energetic or gentle. If the smoothing right after the handoff had strong ripples in spacetime, you might expect a swirl that's easier to see. If it was gentler, you might expect the swirl to hide near the edge of detectability. The no-boundary idea itself doesn't force a loud swirl. It permits a range. That's a feature in practice. As measurements get cleaner, that range is either cut down or left alone. If a swirl appears with a strength and size dependence that only a very punchy early stage would allow, the more energetic corners of the no-boundary neighborhood gain weight. If the swirl continues to hide, the gentler corners are favored. Either way, you aren't saved or sunk by a single flourish. You are graded by how well the whole package fits. At this point, you might worry that no boundary sounds like a label you could slap on anything. It isn't. It forces the earliest region to be compact and smooth in a very specific way. That choice has consequences you can run to the sky. When the classical stage appears, the large-scale geometry must be close to flat over the patch we can see. That is exactly what multiple lines of evidence say in practice. Triangles add up as expected. The ruler in the galaxy distribution sits where it should when you combine it with the distances from reliable beacons. The afterglow's own statistics point to the same wide, almost uncurved stage. If our sky consistently showed a measurable bend across independent methods curved like a ball, or curved like a saddle, the no-boundary start would be under pressure. The fact that it doesn't, within tight margins, is a quiet vote in favor. Another consequence lives in the largest scales of the afterglow. Some beginnings that go through a contraction and rebound leave a faint pattern at the very biggest sizes, a kind of gentle beat. A no-boundary start doesn't naturally insist on that. It leans toward a very plain, almost feature-free speckle, even at the broadest patches. That means the very largest scales become a test. If a strong, persistent beat were to be confirmed there, you'd have to square that with the no-boundary habit of simplicity. If the largest scales continue to look quietly ordinary as maps improve, the no-boundary flavor sits comfortably. What about the late-time story, where the rune stretching speeds up? A no-boundary start doesn't pick a late-time driver by itself. It sets initial conditions for a world whose later behavior we measure directly. The important part is consistency. Starting from a smooth cap with simple seeds must evolve into a web whose weight, as inferred from the bending of light, agrees with the seeds the afterglow shows under an expansion history that matches the beacons and the ruler. That three-way handshake is where many stories fail. The no-boundary idea isn't a guarantee that the handshake will succeed. It still depends on how the early classical stage behaved, but it doesn't put a thumb on the scale in a way that makes the handshake impossible. It gives you a clean slate. The later facts write themselves onto it. It is fair to ask how time turns on in this picture without making it sound like a trick. The answer is ordinary once you stop trying to force a clock all the way down. In the smooth cap, the right variables are not time and space as we use them later. The useful description doesn't divide change along one axis and extension along the others. As the description continues into the classical stage, the world acquires a stable background large enough and calm enough that you can label change in a consistent way. That label time comes from the stage, not from outside it. From this moment forward, the passage looks like history in the usual sense. Before it, asking for history in the usual sense is like asking for north at the exact tip of a pole. The label is not meaningful until you step away. Some people hear no boundary and imagine a final dodge, that you've simply renamed the beginning so you can avoid explaining it. But the test of an explanation in this subject is not whether it names the mystery. It's whether it delivers the right fingerprints to the sky. The no-boundary move is not an escape from work. It is a compact way to produce an initial classical state with exactly the right character. Smooth, almost flat, with tiny, simple irregularities. From there, the work is the same. Carry those irregularities through a bright early world. Let them stamp the afterglow. Measure how they grow into the web. Weigh that web by bending. And keep the whole package in agreement with the late shift in the room's pace. If the package holds, the move has earned its keep. If not, it hasn't. There's also the arrow of time to account for. And here the no-boundary idea earns another quiet point. The arrow is the drift from tidy to jumbled, from smooth to structured, because there are more ways to be a mess than to be neat. A no-boundary start practically forces neatness at the classical handoff. By forbidding jagged configurations at the cap, it selects a very special arrangement just as the stage comes online. That specialness is exactly what the arrow needs. Gravity then does the rest, encouraging structure to grow out of smoothness. You don't need an extra push. You need that early regularity. The no-boundary condition supplies it without bolting on new rules. Could a no-boundary beginning be wrong? In the language we've been using throughout, wrong looks like receipts that refuse to rhyme with its habit of simplicity. If the afterglow's largest patches continue to demand a special beat that can't be softened by better cleaning or by small tweaks downstream, the pressure rises. If we saw strong, persistent departures from coin flip randomness in the speckle that point to complicated ties at the handoff, not to later growth, the story would strain. If the geometry of space were to show a consistent bend across several kinds of measurement, beyond the already tight limits, it would push you toward versions of the beginning that handle curvature differently. If the ancient swirl in the afterglow's light turned up at a volume and a size pattern that can only be made by an early classical stage, far punchier than a no-boundary start tends to prefer, you'd have to reconcile that or give way. None of these are one-strike bands. They are places where the idea's natural preferences meet the world's habits. The world wins. You can also look for the kind of right for the wrong reason that ruins a good story quietly. Suppose a no-boundary model is tuned so that it matches the afterglow perfectly, but requires add-ons later odd ingredients in the early plasma, hidden direction mix, special moves in the growth of structure to keep the web and the bending in step. That is not a triumph. The whole point of starting smooth and simple is to avoid a cascade of fixes. A no-boundary start that leads to simple seeds, only to spend the rest of the script paying for that simplicity with exceptions, is not doing its job. The best version keeps the number of moving parts low from start to finish. It's fair to ask how this kind of start sits next to inflation, the smoothing engine we described earlier. In the cleanest versions, they sit comfortably. A no-boundary beginning hands the classical stage an initial state that is smooth and regular. An early burst of rapid smoothing, if it happens, then keeps curvature and leftover wrinkles under control and stretches the seeds into a readable pattern. The two aren't rivals. One sets the boundary condition. The other is a dynamical phase within the classical story. In practice, some no-boundary calculations also assign weights to classical histories with different amounts of early smoothing. If the weights favor histories with enough smoothing to explain our sky, that's good news. If they favor too little, you either adjust the details of the early engine or learn that this version of the no-boundary scheme prefers a kind of universe we do not live in. That is a useful outcome. It lets you trim the family of starts honestly. There's a different pairing to consider as well. The no-boundary idea versus a rebound after contraction. The rebound picture carries the responsibility of keeping the contracting phase smooth enough and the turnaround gentle enough that the tiny irregularities make it through without being mangled. It sometimes predicts a faint pattern at the very largest scales. The no-boundary picture carries no contracting phase and therefore has no scars from it. Its largest scale preference is for quiet. The deciding ground between them isn't taste. It's the patient improvement of the largest scale maps and the hunt for any clean, ancient swirl in the afterglow's light. If those turn decisively one way, attention follows. If they remain ambiguous, both routes remain in play, and you let the rest of the receipts carry more weight. A practical advantage of the no-boundary start is how it keeps talk about cause honest. In a regime where time hasn't yet turned on as a useful label, asking for a prior cause is a mismatch. The right question is whether the link between the pre-classical cap and the classical stage is lawful and yields a state consistent with the sky's rules. That link is what you can hope to compute. The rest, the final, why these rules, lives outside the current reach of the subject. You don't have to pretend it's solved to do solid work on the part that is. If you want to see how the no-boundary idea shows up in pictures, and not just in words, follow a simple track. Start with the afterglow temperature map, nearly uniform, with tiny variations whose strength across sizes draws a smooth curve with a small lean. A no-boundary start expects exactly such plainness. Look at the afterglow's orientation pattern. Most of what you see is stretch-type structure, with any ancient swirl, either very faint or absent within current limits once you clean away lensing and dust. That's compatible with a range of smoothing intensities that sit comfortably beside a no-boundary start. Look at the counts of galaxy pairs at different separations, a tiny bump at a particular distance, the ruler found at multiple epochs and in harmony with the expansion story read from other beacons. A no-boundary start doesn't fight that. It predicts no special manufacturing of structure that would move the ruler around. Look at lensing maps, a faint, coherent shear that weighs the web in a way that agrees with growth from simple seeds. Again, nothing in a no-boundary start demands exotic adjustments. It leaves room for this entire chain to work. There are refinements you can look for that are subtler than headlines, but still decisive in the long run. The afterglow's largest angular scales are 1. If future, cleaner maps keep showing an unusually quiet level of roughness at the very biggest patches. And if that quietness holds across different parts of the sky and different ways of stripping out foregrounds, it leans toward a start that naturally prefers simplicity at those scales. And no boundary habit does. If, on the other hand, a repeatable pattern emerges at the largest scales that can't be mocked up by local dust or instrument quirks, a pattern that looks like a beat rather than a quiet plainness, then versions of a rebound path gain weight, and no boundary versions that cling to unbroken plainness lose it. That's not drama. It's adjudication by map. You might worry that this way of talking is too depending on, as simple as possible, that it is sneaking in a bias for neatness. But the bias isn't aesthetic. It's empirical. The sky keeps rewarding models that assume less and explain more. The afterglow resists complicated seeds. The web's statistics reward basic growth from plain beginnings. The lensing maps, as they sharpen, line up with the simplest expectations more readily than with Baroque variations. It's always possible that the next decimal place will force extra ingredients. If so, you add them. Until then, you keep the start spare because the receipts ask for spare. One last point matters to anyone who feels uneasy until they can hear what no boundary says in the language of everyday cause and effect. Think of it as an answer to when did history begin, rather than what happened before. In the no-boundary picture, the conditions that make history a useful concept, the presence of a stage that supports a clock and admits a reliable label for change, come into being as part of the same passage that hands us simple seeds. Before is not the right kind of word to attach to that passage. The right statement is that the passage is lawful, that it produces a classical world with a particular kind of earliest state, and that the marks of that state can be read now. It's not an invitation to mystical language. It's an invitation to look at the sky. So, taken without gloss, the no-boundary idea offers a beginning that avoids a sharp cliff, hands the classical world a state that is as smooth as the evidence demands and as imperfect as structure requires, and then gets out of the way. Gravity, chemistry, and light do the rest. It neither promises a fireworks display in the first usable moment, nor requires one. It promises a clean handoff and a plain seed pattern. If that promise keeps lining up with the afterglow's quiet speckle, with the near-flat room we move in, with the ruler etched across galaxy maps, with the gentle bend of far light, and with the later speeding up of the stretch, it keeps its seat at the table. If the sky asks for something else, louder beats at the largest scales, a swirl that shouts, a geometry that refuses to lie flat, then the no-boundary versions that can't adapt step aside. That is the right sense in which it's a scientific proposal. It doesn't win because it sounds serene. It wins when it draws a short line from a compact, regular earliest region to a stack of independent measurements that agree with each other. And it loses the same way, by conflict with the stack. In the meantime, it gives you a way to think about from nothing, without pretending that there was a before to catalog, and without leaning on a singularity that would have to be patched later. You get a start you can say aloud without wincing. No sharp edge in the past, a lawful continuation into a classical stage. Simple seeds laid down as part of that continuation, and a sky that still remembers. There's another way to talk about a beginning that doesn't lean on a before, and it keeps the same promise we've made so far. No metaphors standing in for mechanisms, and every claim tied back to the sky. In this version, the first usable patch of our universe doesn't unfold smoothly from a rounded cap. It appears by a lawful jump. Jump here isn't a dramatic word for magic. It's a simple way to say that the description switches from a pre-classical regime, where before and after aren't good labels, to a small, smooth, already expanding patch of classical space. The jump is allowed by the rules. It doesn't need a backstage shove from a time that doesn't exist yet. From that patch, the rest of the story proceeds, as you already know. Tiny, plain seeds, a hot, bright beginning, the baby photograph, gravity's long patience carving the web. If jump makes you think of particles slipping through barriers in a lab, that's not far off as a picture for what's going on mathematically. But the scale is different and the stakes are larger. The idea is that the pre-classical description assigns weights to possible classical beginnings. Among all the ways a classical patch could look, the simplest are given the highest weight. Smooth, tiny, gently expanding, with no jagged edges or favorite directions. The jump is the transition from possibilities to an actual expanding patch. You don't ask what happened before, because the regime where before is meaningful hasn't begun yet. You ask whether the transition is lawful, and what it leaves behind that we can read now. What it leaves behind, if this is the route, looks comfortingly familiar. A tiny pattern of irregularities laid across a very even background. The power of the jump picture is not that it invents new fingerprints. It's that it naturally favors the same simple seed family that the sky keeps insisting on. The bumps are nearly the same strength over a wide range of sizes with a mild lean. The ups and downs are close to coin flip random, with very little built-in structure, and there's no preferred direction smuggled in. The jump also tends to hand the patch a brief spell of very steady expansion right away, so that any leftover curvature or clutter is diluted. That's how you get a near flat stage and a baby photograph that is almost the same in all directions. From the viewer's seat, the first thing that makes this picture credible is how easily it earns its place in a ledger you already trust. The early chemistry of light elements times the heat and density at the right moment. The photograph wraps the sky with a soft speckle, whose strength across sizes draws a smooth line with a small tilt. The galaxy web that grows later has the texture you'd expect if those seeds were set early and then left to amplify. The faint ruler and echo of early ringing sits where it should. The weight of the web, red from the gentle bend of background light, lines up with what the seeds would have grown into by now, and the late time stretch speeds up in a way that has to be folded into every line drawn from us to the photograph. The jump picture is not a separate story pasted on top of this. It's a claim about how the first frame of the classical film shows up. If it's the right claim, it vanishes into the background once it has handed you the seeds and the wide, level stage. Folding this into everyday language isn't hard. Imagine a catalog of allowed first frames for a classical stage. Small, smooth regions that could start to expand. The rules give each frame a weight. Frames with knots, corners, or built-in directions get suppressed. Frames that are smooth and simple get preference. A jump selects one of the simple frames. From that simple frame onward, you don't need any special moves. The hot, dense plasma forms, light bounces off free charges until the fog lifts. The baby photograph is taken with the seed speckle already imprinted, and gravity begins its long making of the web. Nothing about this requires a spark from a time before time. It requires the rules to permit the jump, and the jump to prefer simplicity. Simplicity, as always, is a strong word only because the sky has defined it for us. In this context, it means a seed pattern with no hidden picture, almost the same roughness from big patches to small, and only a slight lean that makes larger patches a little rougher on average than smaller ones. The baby photograph is where you test that at once. If the jump favored some Baroque pattern rings or grids or strong ties between distant patches, you'd see it. If it favored bumps that were too loud at one size and too quiet at another, you'd see that too. What you actually see is the blandness you need, a speckle that refuses to pick a favorite size or a favorite direction, and correlations that hover a hair's breadth away from perfect coin flip behavior. That is the kind of blandness a jump into a simple frame is designed to give you. The geometry of the room is the next check. A jump into a small, smooth, already expanding patch tends to iron curvature down quickly, because early expansion is very steady. Leftover bend gets diluted the way a drop of dye disappears in a bathtub. Over the patch we can see today, triangles add up the way school taught you. There's no loud spherical bend or saddle-like warp shouting from the largest scales. You can fold that fact into the story without straying. The jump gave you the kind of beginning where early steadiness is natural. And early steadiness is exactly what turns bends into footnotes. There is an optional extra to watch for, and it's the one place a jump story can show some personality without breaking its own rules. The very act of selecting a classical patch with a particular kind of early steadiness may, in some versions, add a whisper of preference for tiny ripples in space itself, right at the start of the expansion. If those ripples were strong, they would leave a swirl-like pattern in the orientation of the baby photograph's light. Separating a truly ancient swirl from the swirl that later bending and local dust create is the hard work we've already talked about. You don't get to skip it. But if a clean, ancient swirl were seen at a level that matches a gentle, steady early stretch, you'd have a fresh way to tie the jump directly to a number. If it keeps refusing to appear as the maps get cleaner, the versions of the jump that rely on a puncher early stretch slide to the back of the shelf. Either outcome is a sober update, not a crisis. A different kind of optionality appears if you imagine that the jump doesn't just create a lone expanding patch in a calm sea. Instead, it pops a patch out of a pre-classical catalog in a way that allows many such patches to appear with different details. You might hear people talk about bubbles, but the word isn't important. What matters is how you'd know about any of this from our sky. If other patches can collide with ours early on, they might leave faint, disc-like bruises in the photograph's temperature map or in its orientation. If the jump tends to turn on with just a little leftover curvature, the room might be ever so slightly open, a kind of bend that's hard to see, but not impossible, if you combine many independent measurements carefully. We don't see convincing bruises in the clean maps. We don't see a persistent, coherent leftover bend across methods beyond very tight limits. Those absences aren't a disappointment. They are part of the data that keep the jump picture modest. If there are many patches, they haven't obviously bumped ours in a way we can detect, and the one we live in looks close to flat. The day-to-day tests, though, are much less about exotic extras and much more about whether the jump delivers. The same seed story the sky keeps asking for, and whether the rest of the chain runs without special pleading. Start hot and dense at the right time, so the early chemistry works out. Hand the photograph a speckle with the right shape across sizes. Stop yourself from painting hidden arrows or grids onto that speckle. Let gravity grow the web in a way that lines up with the bend of light and the faint ruler in the statistics. Sit comfortably with the late time speeding up of the stretch. Because every sight line from us to the photograph passes through that change of pace. A jump picture has nothing to boast about if it can't do those ordinary things effortlessly. There are criticisms that show up whenever this route is discussed, and they're worth airing plainly. One is that a jump is just a fancy way to say something happened without a cause. That complaint only makes sense if you insist on using the word cause in a setting where it doesn't fit. In the pre-classical regime, before and after aren't meaningful labels. The right question is whether a transition from a pre-classical description to a classical patch is lawful, and whether the transition assigns reasonable weights to the simplest patches. If it does, you can push it to the sky and see whether the seeds it prefers are the ones we read. That's not cause in the afternoon talk sense, but it's the right kind of link for a subject that starts working the moment the stage exists. Another criticism is that, with the wrong choices under the hood, a jump picture could be made to fit too much. If you allow it to weight classical patches any way you like, you can always award the winner's ribbon to the seeds we already see. That would be bad practice. The cure is to lock in the weighting before you compare with the sky. If the weighting favors too fancy seeds, the photograph will say no. If it loves gentle, nearly scale-free, almost random seeds with a small lean, the photograph will say yes. The honest flavor of this route is the one that can make that call and live with it. A third criticism asks whether the jump just pushes the mystery down a level. Why this set of pre-classical rules and not another? That's the same edge we met in other routes. The answer is patient. Until you can write a serious account of why these rules, you keep pressing on. How these rules show up in the sky. Every time a route to the first frame survives a new test, the range of acceptable pre-classical habits gets narrower. Every time a route fails, the range moves. You're not dodging the deepest. Why? You're building a fence around it. There's also a reasonable worry that a jump picture might be too eager to produce small expanding patches, leading to a patchwork too wide to talk about sensibly. Again, the sky doesn't let this drift. If a restless patchwork changed the odds for what we should see here, if it sprinkled a preference into our seeds, or if it left repeatable signatures of past encounters, we would be obliged to include that. So far, the photograph is quiet about such signatures and the large scale. Geometry refuses to curve in a way that would flag leftover bend. That tells you what kind of jump picture stays healthy. One that makes our patch simple and minds its own business about the rest, unless the rest changes our numbers. It helps to walk this through once as a continuous story that someone could storyboard without stopping for footnotes. The description begins in a regime where you don't talk about ticks of a clock. You write down rules that assign weights to classical first frames. Simple frames, small, smooth, gently expanding, free of special directions. Get the biggest share of weight. A jump selects one of those frames. Instantly, the labels before and after become useful because the stage exists. Very steady early growth iron downs bend and leaves the room close to flat over the patch we will later survey. The handoff sprinkles tiny advantages in a way that is as plain as you can make it, while still allowing a slight lean across sizes. The universe is hot and bright. Free charges bounce light everywhere. The fog lifts when atoms form. The baby photograph freezes the seed speckle in place. Gravity then does what it always does. It turns small head starts into structure, sketching the web over billions of years. A faint ruler is written into the statistics of galaxy separations, remembering the early ringing. Light that travels across the web is bent just a little, letting us weigh the landscape without asking galaxies to self-report. Meanwhile, the pace of the stretch changes at late times, and every line of sight back to the photograph has to cross that change. You read all of this off the sky, and you ask whether the jump that started it makes the reading easy or awkward. If it makes it easy, the jump stays. What would decisively wrong look like for this route? Start with the baby photograph. if it revealed a strong, repeatable pattern that couldn't be cleaned away by better maps and better modeling of dust, say, broad rings with a fixed spacing, or a loud preference for one band of sizes over the rest, then a jump that favors plain seeds would be in trouble. If careful combinations of measurements said the room really has a coherent bend beyond today's tight limits, and the bend showed up in more than one way of looking, then a jump picture that naturally flattens curvature early would strain to keep its footing. If a clean, ancient swirl in the photograph's orientation turned up with a strength and size pattern that only a very punchy early stretch could make, and if that punchiness couldn't live comfortably with the web, the ruler, and the beacons in the same breath, then a gentle jump picture would step back while a more energetic cousin stepped forward. None of these would be settled by taste. They'd be settled by numbers. There's also the death by 1,000 patches that comes from surviving each test only by adding a special move. If the only way a jump picture can match the photograph is by dialing the seed lane just so, and the only way it can match the web is by sprinkling extra ingredients into the early plasma, and the only way it can match the lensing weight is by changing growth rules late, then it has stopped being a story and started being a collection of excuses. The whole reason to start from a simple first frame is to avoid this. The winning version is the one where one short set of sentences keeps passing in several places at once. If you're listening with a producer's ear thinking about what you would actually show while saying all this, the images don't change much from the other routes. And that's the point. You'd still show the baby photograph with its near uniform background and faint speckle. You'd still show, for orientation, how the speckle's strength across sizes makes a smooth curve with a slight lean. You'd still show the polarization map and explain once how a true ancient swirl would be identified and why it matters. You'd still show a galaxy map becoming a filigree of filaments and nodes, and you'd use a calm overlay to point out the barely favored separation that survives from the early ringing. You'd still show a shape distortion map lensing that quietly weighs the web. You'd still show the plot that says the late time stretch speeds up. The jump doesn't add fireworks. It adds a way to link all these without demanding a before that the stage can't support. At the human scale, the appeal of this route is how unsentimental it is. It doesn't tell you that the universe came from pure absence, because absence isn't a rule you can use. It doesn't tell you that a cause pushed from behind a curtain, because there is no curtain to hide behind until the stage exists. It says the pre-classical description allows a transition, and that the transition picks a simple classical first frame with high weight. It says that from that frame onward, the rest is ordinary cosmic life, hot, bright youth, a photograph that fixes the seed speckle, long, quiet growth into a web, a late-time change of pace that bends every sightline back to the beginning. It promises that if the photograph and the web ever demand more than that, the promise will change. That's as honest as this subject gets. You can feel the arrow of time living inside this route just as easily as in the others. The jump hands the universe a neat stack, a smooth start with tiny, plain imperfections. From there, the drift toward the larger set of arrangements. The scattered pages proceeds. Gravity thickens the web. Stars turn fuel into heavier elements. Planets and chemistry write their own local stories. None of that requires an extra push called time's force. It's the census again, and it began because the start was special. The jump doesn't change that logic. It supplies the specialness in a compact way. What about what's next? This is one version of from nothing in the technical sense. No classical stage yet, but a lawful handoff by a jump into a simple, expanding patch. The no-boundary route you heard in the previous block is another. A smooth cap with no sharp-passed rim, continuing into the classical stage with the same seed story. A rebound after a careful contraction is yet another. Ironing before the turn, a passage through the highest density moment without a break, and then expansion, sometimes with a faint beat left at the very largest scales. Each route uses different words at the front, but the same test at the back. The sky doesn't care which label you prefer. It cares how easily the label can be forgotten once the seeds are set and the stage is wide and calm. And that is the final, practical strength of the jump picture. When it works, it disappears. You don't have to keep reminding yourself that it was a jump. You look at the photograph and the web and the ruler and the bending and the beacons, and you see a single, consistent story that runs forward and backward without straying. If the story keeps holding as the maps sharpen and the catalogs grow, the jump was probably the right way to talk about the first frame. If the story starts to stumble in specific, repeatable ways, if the largest scales develop an attitude that won't be cleaned, if an ancient swirl arrives at a volume that nothing else in the ledger can bear, if the geometry refuses to stay flat within the already tight limits, then the jump will lose ground to whatever handles those facts with fewer moves. You don't have to choose a winner in advance. You let the sky choose slowly on its own schedule. For now, the modest summary is enough. A universe can begin from nothing by a lawful jump, where nothing means no classical stage yet. The jump selects a simple, smooth, expanding patch and lays down tiny, plain seeds. Early steadiness flattens the room you and I live in. The baby photograph freezes the seeds as a faint speckle and a delicate orientation pattern that we can, in principle, isolate from later clutter. Gravity grows the web. The ruler hangs on as a fossil of early sound. The weight of the web shows up in the way distant light is nudged, and the late time stretch changes every line of sight back to the beginning. That's not a slogan. It's a route. If it keeps matching the world, it deserves the space we give it in this story. If it doesn't, we'll trade it for a route that does. The promise is the same either way. No metaphors where a mechanism belongs, and no mechanism that can't be read in the sky. There's a third straight way to tell the beginning without pretending there was a before that you could point a clock at. In this version, the universe doesn't start by switching on and rushing outward. It starts by coming in a slow, disciplined contraction that irons the sheet, makes it even, and then, at very high density, turns around without breaking. After the turn, the same sheet expands. No fireworks, no metaphors dressed as causes, just a lawful rebound that replaces a would-be disaster with a controlled U-turn. Say it in everyday words first. Imagine space not as a room where debris flies, but as the room itself getting smaller in a steady, steady way. When the room shrinks slowly enough, and under the right internal rules, most kinds of unevenness don't get louder. They get smaller relative to the whole. Ripples that would be obvious in a big room become tiny on a smaller stage. Corners round off. The surface becomes almost featureless. That is the key promise of a slow, orderly contraction. It can be a smoothing engine just as effective as an early burst of rapid expansion. It doesn't create, it prepares. A rebound story has 3 jobs to keep, and none of them can be faked. First, the contraction has to favor smoothness. If the wrong kinds of irregularity win, the room collapses into chaos rather than a gentle turn. Second, the turnaround the bounce itself must be lawful. Classical equations predict a crunch if you push them straight through. A rebound replaces that crunch with new behavior that only kicks in at extreme density, so the passage is regular rather than catastrophic. Third, the tiny seeds we need later must be laid down and carried across the turn without being smeared or scrambled. If you lose them at the turn, the baby photograph will never match what we actually see. Take those in order. How does a contraction smooth instead of shred? The trick is in the kind of stuff that dominates as the room shrinks. In most stories, messy features like shearing motions or random lumps would grow and take over. In a good rebound setup, the dominant ingredient during contraction behaves unusually stiff. Its pressure resists change so strongly that it drowns out shear, bends, and wrinkles. You don't need the jargon. You only need the picture. As the room contracts, this stiff ingredient becomes so dominant that everything else curvature, lumps, directional quirks fades in comparison. The result going into the turn is a near featureless stage with only tiny, plane deviations left. That's exactly the state the later universe needs as a starting point. Now the turn. If you push ordinary rules to extreme density, they forecast a breakdown. A rebound replaces that with new behavior that only matters when things are packed beyond any lab's reach. You can think of it as a kind of pressure that appears only when everything would otherwise be forced into a single point, or as geometry refusing to let distances go to zero. However you phrase it, the bounce's personality is modest. It must be stable and brief. It should not paint a new pattern across the stage. It should not pick a favorite direction. It should simply reverse the sign of shrinking to growing without tossing the seeds we need. A good test for any specific bounce idea is whether it leaves the smallest possible footprint. The turn happens, the world survives, and the little irregularities we brought to it come out the other side intact. What about the seeds themselves? In a rebound picture, you don't wait for the turn to lay them down. You build them during the contraction. The slow squeeze gives simple, small amplitude bumps the chance to form with the right spread of sizes and strengths. The important thing is that the bumps be plain, almost the same roughness across a wide range of scales with a small tilt, almost as uncorrelated as coin flips. No secret arrows or grids. That's the same plainness the afterglow prefers. If your contracting phase writes seeds that love one particular size, or if it ties distant regions together in a complicated way, the baby photograph will call you out immediately. Of course, none of this matters if the seeds don't survive the turn. The bounce has to be a clear bridge, not a blender. That's the part theoreticians fuss over, because it's where details matter. If the variables that carry the seeds across the turn couple too strongly to the mechanics of the bounce, you smear the pattern. If they couple in the right measured way, the pattern sails through and begins the expanding era right where it left off, just on a stage that's growing rather than shrinking. In plain terms, the bounce is a gate. The seeds are a password. The universe should walk through with its password unchanged. Put the pieces together, and the post-bounce story feels familiar. The room now expands. The hot, bright plasma forms. Light scatters off free charges until the fog lifts. The baby photograph is taken with the seed speckle already written on it. Gravity spends billions of years amplifying those tiny advantages into the web. Filaments, clusters, wide quiet spaces between. A quiet ruler of faint preference for one separation survives in galaxy statistics as a fossil of early sound in the hot plasma. Light that crosses the growing web arrives to us just a little bent, letting us weigh what lies between. And at late times, the pace of the stretch changes in a way we measure independently and must include when we draw any line back to the beginning. A rebound doesn't dodge any of this. It must make it look easy. What would make the rebound distinctive? In small, careful ways, its hand sometimes shows. First, because seeds are written during contraction rather than expansion, the relationships among ups and downs can carry a slightly different flavor. Not big neon sign departures. Those would have been seen already, but small. Allowed deviations from a perfect coin flip pattern that show up as gentle biases in how the sizes talk to each other. Second, the rebound can leave a faint beat at the very largest scales, a super soft rhythm that only affects the broadest patches of the baby photograph. If that beat were clean, survived better maps and better foreground cleaning, and had the right shape, it would be a quiet point for rebound stories. Third, and this matters because it's testable, rebound stories tend to produce very little of the special swirl-like pattern in the afterglow's orientation that strong early stretching would make. In short, a rebound expects the ancient swirl to be tiny or absent within reach, expects the speckle to be plain with perhaps a subtle long wavelength lean, and expects no hidden arrows or grids. You can already hear how this rubs against data we have. The afterglow is bland and slightly tilted in the way both smoothing by expansion and smoothing by contraction. Like, the swirl has not been cleanly found at the level energetic early expansion would love, which gently favors lower energy versions of expansion and sits well with rebound versions too. The largest scales in the afterglow have flirted with oddity's low power, hints of asynchrony, but nothing has yet cleared the bar of persistent, clean, and immune to better cleaning. That means rebound remains a live route, not by default, but by fitting what is seen and by risking predictions that can be pushed on as maps and methods improve. A well-made rebound also needs to get along with geometry. Just like a smoothing burst, a slow contraction dominated by stiff behavior tends to iron down curvature. Turn around under control and start expanding, and you inherit a stage that is very close to flat over our patch. That lines up with the multiple, independent ways we see space behaving on the larger scales. Triangles add up like school taught us. The ruler sits where it should when cross-checked against distance ladders. The afterglow's own statistics prefer flatness. If in future we were to find a consistent, measurable bend across methods bigger than today's tight limits, Rebound Story would either have to place that bend at the right level from the start or yield ground to a route that does. But as things stand, almost flat is a comfortable fit. What about the horizon question? The how did far apart places look the same on the baby photograph puzzle? In a Rebound Story, the answer is not that they were flung apart after agreeing. It's that during slow contraction, the distances we call far apart today were once within easy talking range. The room was smaller, signals crossed it more easily, and a shared temperature could be set before the fog lifted and the photograph froze. Again, different language, same job. The photograph's uniformity becomes reasonable. The late-time universe imposes the same non-negotiable constraint on a rebound that it imposes on everything else. The expansion speeds up on the largest scales. You can read this off more than one kind of ruler. Reliable supernova, the faint beat in galaxy distributions, subtle distortions in the afterglow statistics. A rebound does not pick the late-time driver by itself. It hands initial conditions to a world whose late-time pace we determine from observations. The only acceptable stance is consistency. Start smooth, write the seeds, cross the turn, expand, and end up with a web whose weight, as read by bending, agrees with what your seeds should have grown under the same late-time pace that distance ladders and the ruler imply. If a rebound constantly needs extra nudges in 3 different places just to keep these in line, it isn't doing its main job-reducing special moves. This is the place to talk honestly about risks. The first is stability during contraction. If the wrong kinds of unevenness are allowed to grow, the stage can become jagged instead of smooth as it shrinks. The way rebound models handle this is to make the stiff ingredient dominant early enough and strongly enough that shears and lumps never take charge. The second risk is the turn itself. A bounce that depends on finely balanced moves at surreal densities can wobble into a bad place. You test against that risk by demanding that small changes in the setup do not blow up the outcome. The third risk is scrambling the seeds. The turn should be a gate, not a food processor. If the variables that carry the seed pattern across the turn get tangled with the mechanics of the bounce, the baby photograph will come out wrong. A serious rebound picture shows how the seeds are protected during the turn, not by magic words, but by a clear separation between what flips the sign of the stretch and what carries the pattern. There's also a practical question about ingredients. Rebound models sometimes lean on components that aren't part of the late-time lineup, things that make the contraction smooth but must fade afterward. That's not a sin. It's a design choice. The test is that those components should exit the stage gracefully and leave no scars we can't explain. If the only way to make a rebound work is to invoke ingredients that hang around where we don't see them, creating odd behavior in the plasma, twisting the way light traveled to us, or spiking the way the web grew, and the rebound is paying a heavy price. The better versions bring their tools, use them, and put them away before the photograph is taken. How would a rebound lose in a decisive way? The easiest path is through the baby photograph. If a clean, ancient swirl were detected at a level that only energetic early expansion can make, far above what a careful contraction and bounce will allow, that would push rebound stories to the back. If the largest scales in the afterglow developed a persistent, well-characterized pattern that looks like a beat of a very particular kind, and that cannot be washed out by cleaning or explained by late-time effects, you'd have to check whether the pattern matches what healthy rebound versions expect. If it doesn't, that's a loss. If the pattern does, the rebound line gains honest weight. If the geometry showed a bend across methods at a level incompatible with how a slow contraction irons curvature down, that would be a hit. If the seeds turned out not to be as plain as we keep measuring, if strong ties or loud preferences kept surviving better maps, then the entire family of plainly seeded beginnings would take a blow, rebound included. And if a rebound wants to win outright, it would help if the afterglow's largest patches kept showing a small, repeatable deficit in roughness that fits the way a slow contraction writes seeds. If orientation maps kept failing to produce a clean, ancient swirl at levels that punchy early expansion claims, tightening the case for gentle or absent ripples. If new sky-wide maps of the web's weight belt from bending continued to sit in quiet agreement with the idea that simple seeds grew undisturbed from the baby photograph to now under the same late-time pace that distance ladders prefer. None of that is dramatic, because none of it should be. A rebound succeeds, like its rivals, by making several quiet facts hang together with fewer special tweaks than the alternatives. It's worth pausing to be precise about what the rebound does not claim. It doesn't claim that time ran before the bounce in any way we can label with the clock. The contraction is part of the same film as the expansion, played in a coordinate that only becomes a good label once the stage exists and is smooth. It doesn't claim that cycles repeat forever. That's a separate question some people like to glue onto rebounds. It doesn't claim that everything we see now is an echo of previous runs. It claims that a slow contraction can set up the right initial state for this run, and it doesn't claim a free pass on the arrow of time. The arrow is the drift from neat to messy. A rebound sets up neatness at the handoff and lets the arrow point forward, just as in the other routes. How does the arrow look from inside a rebound? During contraction, the universe moves toward a very tidy arrangement, the neat stack with only tiny bumps surviving. That specialness is the seed of the arrow. At the turn, the label time has become useful because the stage is large and calm enough to support clocks. After the turn, gravity writes the familiar story. More options open up than close down. Structure grows out of smoothness, and the drift from neat to messy proceeds. No extra force is added. No new law is invoked. The arrow is the same census argument we used before, except now we understand how even a contracting chapter can feed it honestly. You can push on horizons too, without leaving the plain road. In slow contraction, far apart places today were close enough back then to share information. That's why the baby photograph's uniformity isn't a surprise. It is also why there's no need to rely on speculative features beyond our horizon to set the temperature. The work was done in-house, quietly, before the fog lifted. What would you show while saying all this? If you were cutting a film, you'd show a grid that contracts smoothly without rippling wildly, then eases through a tight turn and begins to expand the same grid, not a new one drawn from scratch. You'd show the afterglow map nearly uniform, with the faint speckle we keep talking about, and you'd linger on the largest scales just long enough to say what would count as a real beat versus what's dust or noise. You'd show the polarization maps and carefully separate the likely lensing-induced swirl from what would count as an ancient one. You'd show the galaxy surveys resolving into the web, and you'd point at the slight preference in separations that plays the ruler's role. You'd show the gentle shape distortions that weigh the web and show they agree with the growth story. You'd show the distance brightness plot for reliable explosions, tracing the late time speed up. None of these visuals need to shout. They're receipts. They're the same ones any beginning has to show. It's reasonable to ask whether a rebound is adding complexity where we don't need it. After all, an early smoothing phase in expansion already explains a lot. The right answer is that the universe gets to tell us how much complexity is necessary, not the other way around. If a rebound can do the same jobs with fewer fragile assumptions, or if it naturally explains a real, persistent feature of the largest scales in the afterglow that expansion-only stories struggle with, it earns attention. If it has to bring a suitcase of ingredients just to keep up, it loses that attention. The sorting isn't personal. It's the same thick with fewest patches test we've been using all along. What about repeatability? The idea that rebounds could happen over and over. That's a separate storyline with heavy baggage. Entropy bookkeeping between cycles. How to clean the slate without cheating. How to avoid carrying scars forward. You don't need cycles to have a clean rebound for this universe. You need one controlled contraction, one lawful turn that keeps the seeds intact, and an expansion that behaves the way our receipts say it does. If cycles one day become testable in a way that changes statistics here, they enter the film. Until then, they're scenery. There's a final practical upside to telling the rebound story plainly. It puts from nothing back into useful focus. In our usage, nothing means no classical stage yet. A rebound satisfies that because the part of the description where time is a good label only turns on once the stage is smooth and wide enough. The contraction phase that set up the turn is not a time before time. It's part of a description that only becomes historical once the stage is ready. The turn is the lawful moment that makes the historical description valid. After that, the rest is the familiar chain. Photograph, web, ruler, bending, late time pace. So the honest summary is simple. A rebound origin smooths by shrinking first, sets tiny, plain seeds during that calm squeeze, crosses a lawful turn at high density without breaking, and expands into the world we can still read today. It aligns with the baby photograph's bland speckle and slight tilt. It sits well with a near-flat geometry. It doesn't demand a loud primordial swirl in the afterglow's orientation, and is comfortable if that swirl stays hard to find. It keeps the faint ruler in the galaxy distribution safe. It lets the web's weight and the afterglow's seeds agree under the same late time. Expansion story we read from reliable beacons. Where the largest scales turn up clean and quiet, it smiles. Where they carry a real beat, it has room to talk. Where a loud ancient swirl appears, it gracefully gives ground. No slogans are needed to make that appealing. The appeal is that the same 3 moves define your start, carry its tiny differences forward, and read them back from the skywork, just as well in a world that rebounds as in a world that smooths while expanding from the first frame. Different front door, same hallway, same audit at the exit. If the maps keep tightening and the receipts keep agreeing, a rebound will keep its place in the story. If the sky asks for features only the other routes can provide, a rebound will step aside. The comfort, either way, is that the decision won't be made by taste. It will be written quietly in the light that left when the fog lifted, and in the web that grew as gravity did what it always does. Take small head starts and make them into the structure we live inside. The tiny bumps at the start don't mean much until you see how they travel. What matters is the route those bumps take through a young, bright universe, and how their trail hardens into things we can actually measure. Once you see that chain of custody, from nothing, stops being an argument and becomes a map. begin where the light was still trapped. The early universe wasn't dark. It was too bright to see through. Free electrons were everywhere, and light scattered off them so often that a photon could barely get a step in before it was kicked sideways. In that hot fog, matter and light moved together as a single, tightly coupled mix. If a region was just a hair denser than its surroundings, gravity tugged inward, pressure pushed back. The result was not collapse, but ringing true sound waves in a medium most of us never imagine as an instrument. Where there was a slight excess, the mix tried to compress. Where it overshot, it rebounded. Those back and forths left timing marks that were the same everywhere because the rules were the same everywhere. The tiny seed bumps from the handoff, those plain, almost equal strength irregularities, were the notes. The bright fluid played them. In some places, a crest was midway through squeezing when the universe was at a particular age. In others, it was midway through rebounding. That phase, where the wave was in its cycle, mattered. It meant that when the fog finally lifted, the sky preserved not only how big the bumps were, but also what the ringing was doing at that moment. The fog lifted when the crowd of free electrons thinned enough for light to stop bouncing like crazy. Electrons were captured into neutral atoms. The air quotes around room stopped being a joke and became a way to talk about a clear line of sight. Light began to travel freely. It flew out in all directions, carrying with it a record of the last time it had scattered. That last time wasn't the same everywhere. It was a skin with some thickness, like a photo shoot that wraps over a week rather than a single flash. But on average, it happened at one particular age, and the escaping light wrote down what the bright fluid looked like then. That snapshot is the baby photograph we keep referring to. It's almost perfectly even, but not quite, and the not quite is the story. Slightly warmer and slightly cooler spots are stitched across the whole sky in a pattern that mirrors those seed bumps, seasoned by the ringing that happened just before the fog cleared. There is also a record in the way the light is oriented. As light scattered off electrons, it picked up a preferred direction whenever the surrounding pattern had a certain kind of stretch built in. That preferred direction survived as a subtle polarization. The light's temperature map and its orientation pattern are two views of the same history. The seed bumps, the ringing, the moment of release. The ringing left another, quieter signature that only shows up later when you sift through the positions of galaxies. Because some ripples had reached a fixed distance from the origin. When the fog lifted, matter carried a faint memory of that distance. Billions of years later, after gravity had gathered matter into halos where galaxies could form, there was still a tiny uptick in the chance that two galaxies would sit that particular separation apart, compared with slightly nearer or slightly farther. You don't see it in a photograph, but you feel it in the statistics when you count millions upon millions of pairs. That preferred separation, the frozen note from the ringing, became a standard ruler. When you find it at different look-back times, you're reading how fast the room has been stretching between then and now. Once light was free, gravity began its long, patient work on the matter itself. Regions with the slightest head start, just a hair denser pulled a little more strongly. Neighboring matter drifted toward them. That drift made the head start stronger, which pulled more matter, and so on. Given enough time, the universe developed a scaffolding. Filaments where matter streamed along intersecting highways, clusters where streams crossed and piled up, and wide, quiet voids that were left between. From far away, the pattern looks like lace. Up close, it's a census of halos, each a nest where gas could cool and settle into a galaxy. The key is that nothing in this growth stage is arbitrary. Starting from plain, nearly scale-agnostic seeds, the same roughness across sizes with a small lean, you get a web whose global texture is predictable. The amount of clumpiness as a function of scale follows a smooth curve. The abundance of rich clusters falls off in a way that tracks how long gravity has had to work. The tendency for galaxy triplets to form certain triangles, more often than others, can be read off the same seed pattern after you account for the bias that galaxies are not perfect tracers of matter. Even that bias is tame. On large scales, galaxies are faithful enough that you can treat them as a slightly rescued map of mass. You don't need a new rule at every turn. You need the one rule applied patiently. Even while all of this unfolded, light kept crossing the developing landscape. It didn't charge straight and true. The average pull of the matter between a distant source and us bent its path a little, never enough to make a dramatic arc in a backyard telescope, but enough that, when you stack the shapes of huge numbers of background galaxies, you see a faint, coherent preference in the way they appear, stretched or sheared. That preference is not a quirk of the camera. Teams model their optics and their atmosphere, and compare independent instruments until the only thing left is the sky's own nudge. That nudge, weak gravitational lensing, lets you weigh the web without caring how bright its pieces are. It's the third copy of the seed story. One copy in the baby photograph, one in the web's layout, and one in how the web distorts light on its way to us. There is one more layer, quieter still. That shows up when you compare the baby photograph with far-off structures at later times. The large-scale pattern of bumps and dips in the photograph is not static after release. It's seen again in the way those patterns project onto massive structures along the line of sight. If the expansion speeds up, the deepest wells and highest hills in that large-scale pattern don't hold on to light in quite the same way, and a tiny correlation appears between the photograph and nearby maps of the web. People call that a late-time imprint. You can think of it as a soft handshake between early and late. It's one more way the route from seeds to sky stays connected. The charm of this chain is that you can break it into pieces to test each link on its own terms. Start with the baby photograph's temperature map. If the seeds at handoff really were plain no favorite direction, no hidden tied togetherness, then the map should be describable with a simple recipe. Add up smooth waves of many sizes with independent weights, with a slight lean that gives a little more power to big sizes than to small. When teams fit that simple recipe to the map, it lands right where it should. If it didn't, you could accuse the handoff of having been complicated when it claimed to be plain. Turn to the baby photograph's polarization. If most of the oriented stretch is really the kind that comes from the same waves that set temperature differences, you should be able to predict the stretch-like orientation once you know the temperature map and the simple seed recipe. And if you subtract that predictable part and clean away the contribution from later lensing and from dust in our own galaxy, any leftover swirl-like pattern should be tiny within current limits if the earliest classical moments were gentle. That's what the data say so far. Stretch shows up where it should. Swirl stays small after cleaning. That again fits the plain seed story without pleading. Now leave the early light and count the web. The seed recipe that fit the baby photograph implies a certain smooth curve for how lumpy the universe should be as a function of scale today. Surveys that count galaxies by the million and billion, with careful corrections for what a telescope can and can't see, recover that same curve when they look on scales where galaxies are honest tracers. They also see the faint bump from the frozen note of early ringing at the separation you expect if the room has been stretching at the pace implied by other data. That bump isn't loud. It's a whisper that gets clearer the more pairs you count. But it's there, and it's steady across methods. If it weren't, something upstream would have to give. Either the seed recipe was wrong, or the way we think gravity grew those seeds into the web needs fixing. Or the late-time stretch story has a twist we've missed. Weigh the web by bending next. Weak lensing sees mass, whether or not it glows. It's sensitive to everything the light passed, not just to what made it into catalogs as galaxies. When you reconstruct the mass map from those tiny, coherent shape distortions and compare it to what you'd expect given the baby, photograph seeds and the web's counted statistics under the same late-time expansion, you find quiet agreement within the known margins. That agreement is not automatic. The bending depends on an integral along the path of light, how much mass sat, where, at which distance, while the Webb counts live at specific look-back times and the baby photograph sits at a single, much older slice. Getting those three to sing the same song is a high bar. The fact that they do is why the chain feels trustworthy. Distance markers tie the story together across time. Certain stellar explosions reach a predictable maximum brightness once you've corrected for a couple of details. When you see one in a far galaxy, you can infer how far it is by how dim it appears. Plot enough of these, and you can read how the expansion is pacing itself, especially at relatively recent times. Those plots combined with the ruler from the galaxy statistics say the late time stretch is speeding up. That change of pace affects the interpretation of everything else. It tells you how light from the baby photograph was redshifted on its way to us, and how quickly the Webb was able to thicken. You don't get to pick a different late time story for each dataset. The same change of pace has to be folded into all of them. The early chemistry sets the clock on the other end. In the hot, dense conditions before the fog lifted, the universe forged a specific mix of light elements. That mix is sensitive to how fast the room was stretching when it was a fraction of the age it had at release of the photograph. Measure those abundances in places that haven't been significantly polluted by later stellar activity, and you get a consistency check on the timeline. So far, the forged mix supports the same temperature for the baby photograph and the same early pace that the other pieces point to. Again, this is not a flourish. It's one more link that could have failed and didn't. There are quieter checks hiding in the details. Very small-scale ripples in the bright fluid were washed out just before the fog lifted because light could wander a short distance and gently blur things. That soft blurring shows up in the baby photograph as a damping of speckle on very fine angular scales. It sounds like a footnote, but it helps fix how tightly light and matter were dancing together in the last moments before release. That, in turn, feeds into how you interpret the ruler later on. Another quiet check is the way the baby photograph sky is a little less rough on the very largest scales than the simplest recipe would predict. Whether that is a meaningful quirk or the natural variance of one sky is still being argued carefully. How that argument ends matters for which beginnings you favor, but it doesn't touch the basic chain from seeds to sky. If you step back and try to say the whole route without pausing for side roads, it fits in a paragraph. Seeds are laid down at the handoff. Tiny, plain, almost the same strength across sizes, with a mild lean and no hidden picture. In a hot fog of light and free charges, gravity and pressure make that mix ring like a drum. When the fog lifts, light flies and carries a slightly warm-cool pattern and a subtle orientation record with it. The ringing leaves a frozen note at a particular separation, a future ruler. Gravity magnifies the tiny head starts into a web whose overall texture you can predict if the seeds were as simple as they're supposed to be. Light on its way to us is gently bent by the average pull of everything between, and those bends can be read from patterns in the shapes of distant sources. Reliable explosions and other distance markers time the pace of the late stretch that every line of sight passes through. The early chemistry fixes the heat and density ages ago. The same seed recipe, carried forward under the same expansion history, matches all of it at once. This is why the subject can be patient about disagreements at the edges. When one distance marker disagrees a little with another, or when one map's cleaning of the baby photograph reveals a tiny feature that another can't confirm, the right response is not to throw out the root. It's to trace where in the chain the mismatch lives. If the Webb counts say the world is a little more or less clumpy than Lensing prefers, eyes turn to how galaxies are biased tracers, to how the camera's shapes might have been modeled, to whether the late time pace the distance markers are insisting on has been fed consistently into both sides. That's not nitpicking. It's the day-to-day work that keeps a story honest. One worry you sometimes hear is that this story relies too heavily on statistics, as if that makes it soft. But statistics is not a compromise here. It is the right level of description for a single universe seen in many independent ways. The seed recipe is statistical by nature. How strong the bumps are as a function of size, how tied together or not they are, whether there are favorite directions. Those are the parameters we can hope to measure because the universe gives us only one sky and one web, but fills both with millions or billions of independent samples. A rock can be weighed. A universe can be described. The chain from seeds to sky is trustworthy because so many different statistics sing the same tune. There is also the human side check, how the maps themselves are built. The baby photograph is not a postcard you hold up and admire. It's a data product that emerges from years of staring at the sky in multiple frequencies, subtracting our own galaxy's glow in more than one way, masking out point sources, and doing everything twice with a different set of assumptions to see if the answer holds. The web isn't a pretty simulation passed off as reality. It's a set of catalogs with selection effects that are ugly to look at and vital to correct. What you can see depends on brightness, distance, dust, weather, and the habits of the survey. People build mock catalogs with those same habits and run their counting methods through them to make sure the answers don't depend on tricks of the pipeline. Lensing maps are not optical illusions. They are the leftovers after you've accounted for how a mirror sags, how the air wobbles, how the detector blinks, and then check the answer with a completely different telescope. None of that toil is glamorous. All of it is why the route means something. If you want a feeling for how robust the chain has become, look at how it handles very different kinds of measurement at once. The ruler from early ringing doesn't care about how bright a galaxy is. It cares about where pairs sit. The distance markers care a lot about brightness and very little about pair counting. The lensing cares not at all about either. It cares about shape. The baby photograph's temperature map cares about microwave light and foregrounds. Its orientation map cares about micro-aligned directions and the lensing that distorts them. The early chemistry cares about entirely different observations in entirely different places. Yet when you ask the same handful of seed and expansion parameters to fit them all, they do within quoted margins. That cross-fit is the deepest reason to trust a calm, mechanistic origin over a romantic slogan. It works across languages. The chain also keeps you honest about the future. If a new, full-sky map of lensing weight comes, back sharper and reveals that the web is 5% denser than you thought on certain scales, you don't have the option of changing only the lensing chapter. You have to ask which part of the seed recipe or the late-time stretch story will move and whether the baby. Photograph and the web counts can tolerate that move. If a gentle swirl in the light's orientation is finally cleaned from late-time confusions and shows up at a level that favors a slightly punchier early classical stage, you don't throw that at inflation or rebound in isolation. You check whether the preferred level still lets the web, the ruler, and the distance markers sit together. The chain limits how many knobs you can twist independently. It forces you to live with consequences. None of this changes the humility at the attempt's core. We still don't know why the rules are the rules. We still have three broad ways to talk about the handoff, no sharp past edge. A lawful jump, a rebound, and the sky hasn't stripped the field down to exactly one. But the chain lets us say, with a straight face, that from nothing, in the technical sense no classical stage, yet can be turned into a world we can read. If and only if the seeds are as plain as the baby photograph insists. If and only if the bright mix rang, and then let go in a way that leaves the ruler behind. If and only if gravity was given a smooth enough stage to build a web whose texture matches a simple recipe. If and only if light on its way to us bent by just the right amount. And only if the pace of the late stretch is threaded through all of that. That long string of ifs is the backbone, not a weakness. They are the same ifs that make it possible to be wrong for specific, checkable reasons. You might ask whether there's any room in this route for surprises. There is, but they're the quiet kind that help you choose between beginnings rather than redraw the whole map. A persistent, well-cleaned quirk on the very largest scales of the baby photograph, one that refuses to fade as methods improve, would lean us toward rebounds over no boundary starts, or toward particular settings of a smoothing engine over others. A clean, ancient swirl in the orientation at a definite level would push the energy scale of any early classical stage up or down, trimming families of models rather than overturning the enterprise. A small, consistent mismatch between the web's weight measured by bending and its expected weight from seed growth under the already measured late-time pace would start a hunt. Is it the reading of the seeds, the fairness of galaxies as tracers, or the treatment of the late-time driver? Each of these surprises is a way of tightening the chain, not snapping it. It's worth saying one last time, in plain words, what the chain makes of that headline phrase. From nothing is not a boast. It's a translation. It means from a regime with no classical stage yet, through a lawful handoff that lays down tiny, plain seeds, into a world where those seeds can be followed. Follow them, and you get the baby photograph's faint speckle and subtle orientation, the web's texture, the frozen note from the early drum as a ruler in galaxy separations, the gentle bend of light that weighs the landscape, and a late-time change of pace that touches every line to the past. That is not a metaphor for comfort. It is a mechanism that happens to be comfortable because it keeps letting very different facts agree. You could end the segment here, but it helps to take one breath more and underline the practical lesson. If someone tells you an origin story and you want to know if it belongs in a serious film, don't ask whether it sounds bold. Ask whether it makes the seed recipe plain and whether it can carry that recipe to the baby photograph and the web without inventing exceptions. Ask whether it sits easily with the room's near flatness, with the ruler's quiet bump, with the bending's quiet weight, and with the late-time speed-up. If it can, it deserves airtime. If it can't, no amount of charm saves it. From here, the next sensible topic is the bookkeeping that traps a lot of bad arguments. Energy, where it's conserved, and where the common global meter picture misleads, and why gravity's contribution balances the books without creating a universe. The chain we've just walked will keep its shape while we sort that out. Let's clean up the part that trips people most: energy. A lot of arguments about from nothing die in the same cul-de-sac energy can't just appear. Where did the light's energy go as it redshifted? Does dark energy create energy out of thin air? And so on. The cure is simple once you separate two ideas that sound alike but are not the same: local conservation and a single global meter. Locally, the bookkeeping is exact. In every small region, matter, light, and the geometry they live in balance perfectly, step by step. Push here and something pulls there. Heat flows, pressure does work. Momentum is tracked, nothing slips. That statement is as hard-edged as physics gets. It's the reason you can trust the way the early hot plasma rang like a drum, and the reason sound waves froze into a quiet ruler at a very specific separation when the fog lifted. It's also the reason the afterglow still wears a temperature that matches the old heat and the old density. Local balances are the bedrock. The confusion enters when we try to stretch the same habit over the entire universe and ask for one grand energy number that never changes. That only makes sense if the stage itself isn't changing. In a perfectly steady room with the same rules at every moment, there is a clean way to define a single number and shout "conserved" for all to hear. But the cosmic stage we live on is expanding. Distances between resting points grow. The very label we call time translation is not a symmetry of the whole play. When the stage is changing like that, a single global meter is not guaranteed, and in our case, is not available at all. That's not a bug. It's the setting. This is the shortest honest answer to the classic redshift puzzle. As the universe expands, The wavelength of free-flying light stretches. The energy of each photon drops, and the glow cools. Where did the energy go? Nowhere. The question assumes a single global meter that doesn't exist. If you track the light locally as it moves, every tiny exchange and every tiny push is balanced. The drop in energy of the light is not a transfer to some other bucket you can point at. It's a change in a label that only made sense as a global total in a room that wasn't changing. The local books still balance. The global bank statement was never a thing you could print in the first place. Gravity deepens this divide in a way that helps, if you let it. The energy stored in attracting masses is negative. You can feel that in a simple way. Two objects bound together have less energy than the same two far apart. They had to shed something like heat, motion to bind. Translate that instinct to the largest scales, and a picture emerges in which the positive energy of matter and light can be balanced locally and properly by gravity's negative contribution. In the right sense, the two can cancel. That does not create a universe. It removes the urge to imagine a cosmic cashier paying the bill from the outside. The universe is not a purchase. It is a lawful stage with balances that don't need an external account. You can test every line of that paragraph against the sky. Take the afterglow. Its temperature today, just a few degrees above absolute. 0 is a relic of a time when the glow was much hotter and the wavelengths were much shorter. As the room stretched, the glow cooled. The number of photons in a comoving block stayed what you'd expect. The energy per photon dropped. The density of energy in light fell faster than the density in matter. If you still want to ask, who took the energy? You're putting a single global meter where none can exist. The practical content is that the glow's cooling matches the expansion we read off from distance markers and from the ruler, etched into galaxy positions. That consistency is the win. There is no missing bucket. Now swing the lens to matter. The energy tied up in ordinary mass behaves differently from light. It thins because the room gets bigger. The amount per block goes down because the block gets bigger, not because the mass is evaporating into a mystery fund. When the world was dense and hot, this distinction mattered for chemistry. The early furnace forged helium and a little deuterium and lithium in fixed ratios that depend on how fast the room was stretching at that time and on how much radiation was still carrying the load compared with matter. Measure those ratios in clean environments today, and you get a clock check on the expansion story. It's not poetry to say the numbers agree. It's why you can keep using the same map. What about the piece that makes people the most uneasy? An ingredient that seems to have constant energy density as space grows, what we call a cosmological constant, or dark energy in its simplest reading. If the density stays the same and the room gets bigger, doesn't the total energy keep rising? Yes, if you insist on a total. And no, that isn't a violation of the local balances, because in an expanding universe, there is no single global meter to be violated. Locally, the picture is tidy. A component with negative pressure does work on the stage in a way that keeps the local bookkeeping exact. What the single number question wants, the where did the extra energy come from, is a story that the world doesn't have to tell. The observables we actually test are whether the late time stretch speeds up, how that speed up shows up in the distance ladder, how it shifts the ruler in the web, and how it leaves a tiny imprint on the afterglow statistics. Those are the places where dark energy earns or loses its place. A global meter isn't one of them. Fold that back to the headline. The claim that a universe can begin from nothing, in the technical sense, no classical stage, yet doesn't draw power from a gimmick where debts cancel and a universe falls out of arithmetic. It draws power from a lawful handoff that creates the stage of description and lays down a tiny, simple seed pattern. The energy talk isn't the engine that makes a universe. It is the sanity check that says we don't need an outside bank. Locally, balance is hold as the stage appears and evolves. Globally, there is no single number to hold. Gravity's negative contribution makes the whole picture less nervous, not more. You can spot the same theme in the early smoothing stories. During a brief, steady phase of very rapid expansion, the driver behaves like a reservoir. While the room doubles and doubles again on short timescales, the driver's density barely changes. When that phase ends, the stored energy empties into heat and particles. The world becomes a hot, bright plasma that behaves exactly like the one our later chemistry and the afterglow demand. None of that is energy from nowhere. It is energy from the driver into the contents, modeled in a way that keeps local balances exact. We don't have to like the word choices some papers made along the way to admit that the core picture is clean. The same clarity rescues you from the most common talking point traps. Energy can't be created or destroyed, so the Big Bang violates physics. Local balances are exact. A single global meter is not defined in a stage that is changing size. The very premise mistakes what kind of conservation law the universe has. Photons lose energy as the universe expands. Where does it go? It doesn't go anywhere. The question assumes a global total. The measurable content is that the glow cools with expansion in a way that matches other independent checks. Local balances along every path are intact. Dark energy creates energy out of nothing. It is a component whose local behavior is captured by an energy density and a negative pressure. In an expanding room, a single global total is not a legal invariant. The way to test this component isn't to demand a number the universe doesn't have. It's to ask whether late-time distances, a ruler in the web, and subtle correlations with the afterglow match one story. If gravity's energy is negative and cancels matter, doesn't that mean the universe is free? Sometimes people say zero-energy universe as a slogan. In certain special spacetimes, you can define a meaningful total, and it can vanish. In our expanding case, that move is not available. The useful takeaway is smaller and safer. Gravity's negative contribution removes the need for an external payer. It isn't the mechanism that turns no classical stage into a classical world. Notice how each of these answers pairs a rule with a receipt. The rule is that local balances are exact. The receipt is a piece of sky that only makes sense. If you respect that rule and stop asking for a single global number the universe doesn't offer. Distance ladders, the Webb's ruler, the afterglow's cooling, the early chemistry, they all support the expansion story without a global meter. None of them would be possible if local balances were sloppy. You can make this concrete with a tour through the same chain we've already trusted. The early plasma behaves like a fluid with pressure. As the room stretches, pressure does work, and the energy tied up in the glow falls in a way that fits the observed drop in temperature and the damping of very small-scale ripples in the baby photograph. When the fog lifts and photons fly freely, their wavelengths stretch with the room, and the spectrum of the glow stays the same shape while it cools. That is the reason the afterglow today is such a perfect thermal curve with a temperature of a few degrees above absolute zero. There is no hidden drain in that story. There is no need for a safe labeled where it went. In the same breath, the early chemical clock checks the speed of the stretch. If the expansion had been faster or slower at the forge time, the abundance of helium and deuterium today would be off by an amount we could not hide. It isn't. The clock and the photograph agree. The energy conversation hiding in that agreement is simple. The contents of the young universe were arranged in a way that made the local balances exact at each step, and the overall expansion was what you can read now in multiple independent ways. No single total explains that. The match explains it. People sometimes reach for a box analogy to reason about energy imagine. Gas in a box with pistons pushing in or out, and then they carry that habit into cosmology with a sneaky mistake. The universe has no pistons and no walls. You can define a first law style balance for a box because the boundary is a thing you control. In a universe, the boundary is not a physical surface. It's a choice of how you draw a big patch on an expanding stage. The only balances that never need you to define a fake wall are the local ones, tiny patches where the equations translate directly into what goes in must come out. That's why physicists are so stubborn about local conservation and so relaxed about global totals only when the stage is steady. It isn't evasiveness, it's good hygiene. Let's also touch the way gravity bends light, because it's the most vivid place where people expect a cost. As a beam passes near a massive structure, its path bends and its frequency can be shifted. The local energy bookkeeping that links the beam's stress to the geometry's tug is exact along the way. When you stack millions of shapes and build a lensing map, you're reading those local accounts back out as a pattern. The map is not an energy bill. It's an audit of how mass was arranged along each sight line. If you insist on paying the bill with a single global number, you'll miss what the map is telling you, that the weight of the web agrees with what the seeds would have grown into by now, under the same expansion history that other receipts demand. Late time acceleration is the other place where energy language gets people anxious. Distances grow faster on the largest scales than they did midway through the universe's life. That is not a license to declare a breakdown. It's a headline about the contents. Whatever component drives the speed up behaves locally like something with energy density that doesn't dilute away in pressure of the pull the stage apart kind. The way you test that statement is not to ask for a global sum. It's to look for the fingerprints of that change of pace in several places at once, in distance brightness plots for reliable explosions, in the position of the web's ruler at different eras, in a tiny correlation between nearby structure and the baby photograph. Those checks are noisy, and teams argue about details, but the picture is stable. The late time story is a speed up. That speed up slides into the route from nothing to now, not as a metaphysical shock, but as a boundary condition you must include in every line you draw back to the photograph. Energy language that respects local balances and drops the global meter is the only language that keeps all those lines consistent at once. There's a comforting symmetry in how this whole subject cleans itself. When someone tries to close the door on the origin by saying, energy forbids it, what they have in mind is a household conservation law that needs a steady stage and a single meter. The universe does not offer that meter. What it offers is harder and better. Exact local balances, a gravity term that counts with the opposite sign, and a stage that changes in a way you can measure from several angles at once. On that stage, a lawful handoff from a pre-classical regime can lay down simple seeds and let the rest proceed without borrowing, without theft, and without a cosmic cashier. The sky doesn't show you a bill. It shows you a chain of matching receipts. If you take the long view, this is restraining rather than permissive. You don't get to plug any story you like into the beginning and claim that the universe's total energy made it free of charge. You have to show that your handoff gives simple seeds, and that those seeds survive into a world whose local balances are exact at every step, whose glow cools the right way, whose early chemistry fits the clock, whose web weighs what it should by bending, and whose late time stretch lines up across methods. Gravity's negative contribution removes a rhetorical obstacle. It does not bail you out of those checks. It's worth looking at how the same discipline cuts away bad rhetoric on the everything is allowed side. You might hear, in an expanding universe, energy conservation doesn't apply, so who cares? That's worse than wrong. It's useless. Local conservation is the thing you most need if you want to trust any calculation that carries seeds from the handoff to the photograph, or that predicts how the ruler in galaxy separations holds its place. Drop local conservation, and you lose the drumbeat, the damping of small ripples, the matching of temperatures across frequencies, everything that makes the data tight. The right summary is boring and strong. Local balances always. Single global totals only when the stage is steady, which it isn't. You can even hear the same note in the arrow of time story we already told. The universe began in a low disorder state smooth with tiny bumps, not because that was cheap energetically in any global sense, but because that is the only kind of start that lets later structure grow in a way that matches the sky. As structure grows, the ways to arrange matter and light multiply. The arrow points from the neat stack to the scattered papers. Energy bookkeeping is not the author of that arrow. It's the grammar that keeps the sentences well formed as the arrow's story unfolds. Where does this leave the headline? Right where we want it. From nothing, translated into the workable phrase, from a regime with no classical stage yet, doesn't have to fight energy. It has to fight a set of receipts. The lawful handoff that turns that regime into a classical world and lays down tiny, plain seeds is compatible with every way we know how to test it. Local balances hold at every step. There is no global meter to forbid the expansion that the beacons and the ruler and the afterglow all demand. Gravity's negative contribution keeps you from inventing an outside budget. The result is not a loophole. It is a route that refuses melodrama. If you want this section's message in a couple of casual lines you can carry around, take these. Stop asking the universe for a single energy number it can't give you while it's changing size. Start trusting the things it does give you. Exact local balances, a glow that cools with the stretch, a chemical clock that keeps the same time as the photograph, a web whose weight matches the light it bends, and a late time pace that shows up the same way in more than one place. With that in hand, from nothing doesn't dodge energy. It passes right by it, on its way from a quiet handoff, with simple seeds to the sky you can still read tonight. If you strip the subject to its working parts, what's left is cleaner than the headline suggests. From nothing doesn't point to a mysterious void. It points to a regime before the classical stage of space and time turns on. From there, a lawful handoff delivers a world you can describe with distances and durations. And that handoff leaves tiny, simple irregularities behind. Everything you have watched us do is the follow-through from that one move. We carried those small differences through a young, bright universe, watched them freeze into the sky's first photograph, and then watched gravity amplify them into the web we live inside. We compared this quiet chain with the records the universe kept, the afterglow's speckle and polarization, the faint ruler in galaxy maps, the web's weight read by the way it bends light, and the late time change of pace that touches every line of sight back to the beginning. The pieces fit not because we forced them to, but because the world seems to have chosen a start that makes fitting possible. That fit makes the headline modest. The beginning is not a firework. It's a setup, a neat state with tiny, plain bumps. In one route, the earliest region has no sharp rim in the past. The useful labels of time and space only switch on as the stage appears. In another, a lawful jump selects a small, smooth, already expanding patch and lets the rest proceed. In a third, the world contracts slowly enough to iron itself flat, turns around without breaking, and expands with its seeds intact. None of these routes asks you to pretend there was a before you could mark with a clock. Each asks you to check whether the same plain seed pattern makes sense of several independent facts at once. And each stays or goes on the strength of that check. The check begins with light that left when the fog thinned and hasn't stopped traveling since. That light paints the whole sky with a nearly uniform wash and a fine speckle. The speckle's strength, as you zoom from large patches to small, draws a smooth curve with a slight lean. Its directions do not hide an arrow. Its ups and downs behave almost like independent coin flips once you factor out what gravity does later. The light's orientation tells another part of the story, a stretch-like pattern you can predict from the temperature map, and a swirl-like pattern that is tiny after you clean away later bending and the dust of our own galaxy. This picture is the most honest record we possess of the first usable moments, and it is ordinary in a way that makes extraordinary claims unnecessary. From that same seed recipe, you can predict what a slow accumulation under gravity should do on large scales, long after the fog lifted. It should build filaments and knots with a texture you can measure. It should leave a whisper of the early ringing, a slightly favored separation, visible if you count enough pairs of galaxies with care. It should weigh what it has built in a way that matches the faint, coherent shape preferences we see when we stack the images of distant sources and measure how their light was nudged. And it should let a late-time change of pace slide into the story without tearing the earlier pages. That is exactly what we observe. A web whose statistics track the simple seed recipe. A standard ruler left by early sound that agrees with distances read from reliable explosions. A bending pattern that weighs the landscape without asking galaxies to self-report. And a late-timed speeding up of the stretch that shows up wherever it should, not just in one kind of measurement. You do not need a single equation in front of you to feel the discipline this imposes. A beginning that loves one size too loudly would bend the afterglow's speckle away from the smooth curve we actually see, and the mismatch would echo later in the ruler and the web. A beginning that hides elaborate ties between distant patches would leave a fingerprint in the photograph that won't wash off, and the photograph refuses it. A beginning that pushes strong ripples into space-time at the first classical moment would write a swirl that's bigger and broader than the one we can find after cleaning. The sky has not granted that permission. A beginning that tries to keep the room's geometry significantly curved would have to fight several independent maps at once. Triangles add up the way school taught you, and the ruler sits where it should once you line it up with the distance ladder. The sky doesn't debate these points. It just shows you the balance sheet. Time itself settles into this balance sheet without any need for drama. Before the stage is stable, before and after are the wrong tools. When the stage arrives, clocks are born all at once. The overall stretch, the cooling of the glow, the thinning of the fog, the steady switch on of neutral atoms, the first unambiguous starlight. The arrow that points from neat to messy isn't a command. It's a census. There are more ways for the world to be jumbled than tidy, and the start was tidy enough that gravity and chemistry could write a long story. A neat stack of papers does not flip into place by itself. It slides into disorder unless you work against the odds. The early universe was the neat stack at a scale we almost never imagine. That fact is not speculative. You can read it directly in the uniformity of the photograph and in the growth of the web. We also did the housekeeping that usually tangles this conversation. Local balances how matter, light, and geometry trade energy and momentum in every small region are exact. A single global meter that never changes is not offered on a stage that is itself changing size. The glow's cooling is not a mystery fund. The density of energy and light falls as its wavelengths stretch, and the story matches the distances and the ruler we read elsewhere. Gravity counts with the opposite sign to matter and light. That removes the urge to imagine an external pair without conjuring a universe. None of this solves the origin. It removes the wrong door so you can walk through the right one. There are, of course, open ends. We have not answered why the rulebook is what it is. We have not proved which handoff is the one nature took, only that several routes no sharp past rim, a lawful jump. A rebound can be written cleanly enough to reach the sky, and that some are pruned as maps sharpen. We have not decided whether regions beyond our horizon settled into habits different from ours. We have said that those questions are allowed to stay open without weakening the core chain, and that when they matter here, they will matter by changing odds and patterns we can actually measure. Multiverse is scenery until it tilts statistics in our patch. High-energy smoothing is a viable accent until the ancient swirl refuses to be seen with the character it would demand. Rebound is a neat idea until the largest patches of the photograph nail down an answer about the quietness or the beat. They carry. The field is not allergic to these words. It's just loyal to receipts. What would feeling wrong look like if it arrived tomorrow? You could imagine a cleaned, multi-instrument map of the afterglow, revealing a strong, repeatable structure at large scales that refuses to fit into any plain seed recipe rings, with a fixed spacing that cannot be ascribed to foregrounds, or to late-time interference, for example. You could imagine a coherent, cross-checked measurement of space's geometry that pushes curvature above today's tight bounds in more than one language at once. You could imagine a swirl-like orientation in the ancient light, clearly separated from lensing and dust, that arise with a strength and size dependence that only the punchiest first moments could make, and that refuses to live in the same room as the web, the ruler, and the distance ladder without tearing something. You could imagine a persistent mismatch between the weight of the web read by bending and the web you predict from growth under the already measured pace, one that survives changes in method and instrument. None of these would ruin the enterprise. Each would push weight from one route to another and force us to rewrite a link or two in the chain. The comfort is that the chain is built to survive tightening. If you prefer one sentence to carry out with you, make it plain and literal. A universe can form from nothing when nothing means a pre-classical regime in which the words before and after are not yet usable. A lawful handoff brings a classical stage online and lays down a tiny, simple seed pattern. Gravity and expansion carry those seeds forward, and the sky through the ancient photograph's speckle and polarization, the web's texture, the quiet ruler in galaxy separations, the gentle bend of background light, and the measured change in the pace of stretchings, still remembers. Every piece of that sentence cashes out as something you can look for, something you can cross-check, something that does not depend on someone's taste and ideas. If you want what remains to be solved, stated cleanly, rather than made mysterious, it's this. We still want a tighter derivation of the seed family from any given route to the first frame, not just a statement that simple is preferred. We still want the largest scales of the photograph to decide whether their quietness is the last word or whether a real, delicate beat belongs in the score. We still want the swirl-like orientation cleaned to the point where a yes or a no on ancient ripples stops moving around with each new map and stays put. We still want full sky maps that weigh the web with enough precision to make petty disagreements over method disappear and to tell us, without hedging, whether the weight and the growth sit exactly where the simple seed recipe would put them under the same late-time stretch we read from other beacons. These are not gaps to fear. They are ways to let the universe say more. Underneath the details is a method that doesn't care which version you're fond of. Don't let metaphors stand in for mechanisms. Don't ask for single numbers the world does not supply. Don't call inevitability what is really stability. Translate big words into small, checkable claims. Ask the same core question of every root. Does one plain seed pattern flow through light, matter, and geometry without a bag of special moves? If it does, it stays. If it can't, it sets down the microphone. That's not an aesthetic choice. It is how you protect a subject that tempts people to improvise. There is also a good way to carry this out of the room and into your picture of everything else. The largest truths we've used are not fragile. Space looks near flat over our patch. The afterglow is near uniform with a gentle, slightly tilted speckle. The web grew from those seeds at a pace that matches a late-time acceleration we read in several languages. And light along the way bent just enough to weigh the landscape as expected. None of these statements pre-decides which handoff won. They set the fence around what winning can look like. If a new favorite arrives that can't live inside that fence, it isn't a favorite. It's a poem. If the story feels quiet compared with the title, that's the right feeling. The world is quieter than the title, and that is a gift. Quiet stories can tie more facts together. They are easier to check. They are easier to replace when they fail. We end with a world that did not need a drum roll to begin, that did not need a backstory outside its own rules, that did not need a miracle where a mechanism would do. It needed a lawful handoff in a seed pattern so simple that lake-time complexity could grow without tripping over its own feet. It needed a sky that kept excellent records. It needed us to read them without trying to make them say more than they do. If you want one last translation of the title that won't wear out with use, keep it short. Universe, the classical stage with space and time. Form, a lawful passage into that stage that sets simple initial conditions. Nothing, the regime before that stage exists. Translate the headline that way, and the entire film you just watched becomes not a promise, but a list of receipts. The receipts don't answer the ultimate why of the rules, and they don't have to. They answer the how well enough that any future why will have a narrow target to hit. The last habit is the one we have modeled over and over and asked you to adopt without making a ceremony of it. When someone offers you a beginning, you don't need to decide whether you like the mood. You need to take 3 steps. Make the terms exact, carry the consequences forward, and look for them where the universe has left them. The subject rewards that kind of attention. It does not reward romance. The sky is patient. It will still be there the next time a better map arrives. The right answers have a way of surviving new instruments and new methods without changing their voice. You can stop here, or you can keep the last line. We promised we would not spend lightly, and spend it once. You know exactly what it means now, because you have seen how every map and every argument translates into it. Propagate the ripples. Check the sky.